At our current speed, it would take a spacecraft over 70,000 years to reach even the nearest star. That's longer than all of recorded human history. And yet, almost every vision of our future, whether in science fiction or scientific theory, assumes that one day we will leave the solar system. Not just with robotic probes, but with living, breathing humans aboard. So, will we? Can we find a way to cross the impossible gulfs of interstellar space? Or are we destined to remain in our solar system forever, like fish in a cosmic fishbowl, able to glimpse the stars but never touch them? The answers lie somewhere between the known limits of our science and the edge of our imagination. Let's explore how close we really are to making the great leap. Measuring the cosmic shoreline. What lies beyond the heliopause? Far from Earth, past the orbits of Neptune and Pluto, lies a silent place where the reach of our Sun comes to an end. It marks one of the most important transitions in space. Here, the solar wind, charged particles constantly flowing from the Sun, slows down and fades into the wind of another kind. The interstellar medium, a thin mixture of gas, dust, and cosmic rays that flows between the stars. This border, known as the heliopause, is the edge of our solar system's influence. Closer to the Sun, the solar wind flows outward at supersonic speeds, creating a bubble around our solar system called the heliosphere. This bubble protects us from some of the harsh radiation of deep space. But as the wind moves outward, it eventually runs into the pressure of the interstellar medium. It slows down dramatically at a point called the termination shock, forming a vast region of slower, heated particles. And then, even farther out, it reaches the point where the Sun's wind can no longer push back. That's the heliopause. For decades, this boundary was only a theory. No spacecraft had ever crossed it. Scientists could model it, simulate it, guess its location, but it remained a mystery. That changed with two remarkable spacecraft, Voyager 1 and Voyager 2. Launched in 1977, these two probes were sent on missions to explore the outer planets. But after completing their flybys, they kept going, coasting on momentum, powered by small nuclear batteries, heading into the unknown. They became humanity's slow ships to the stars. Voyager 1 was the first to reach the heliopause. In August 2012, it crossed the invisible frontier. But there was no camera to capture a photo, no sudden jolt or alert to announce the moment. Instead, the clues came from a set of instruments. One sign came from the cosmic ray detector. Inside the heliosphere, the solar wind carries lower energy particles. But outside, in interstellar space, there are high-energy particles that come from exploding stars, called cosmic rays. As Voyager 1 approached the heliopause, scientists saw the number of solar particles drop and interstellar cosmic rays rise sharply. That told them something had changed. Another instrument, the magnetometer, measured the direction and strength of the magnetic field. The solar wind carries the Sun's magnetic field outward, but in interstellar space, the magnetic field has a different direction. Voyager 1 recorded a sudden shift, proof that it had passed into new territory. There was still one more check. The plasma wave instrument, which listens to the faint hum of charged particles, detected a change in the density of plasma around the probe. Inside the heliosphere, plasma density is lower. In interstellar space, it's higher. When Voyager 1 sent back data showing that the density had risen, scientists were convinced. The spacecraft had broken through. Voyager 2 followed years later, crossing the heliopause in November 2018. Its crossing was even more detailed because Voyager 2 still had a working plasma instrument. It directly measured the density, temperature, and speed of the plasma. Like its twin, it recorded a drop in solar wind particles and a rise in interstellar ones. Its data matched Voyager 1's, though the heliopause appeared slightly closer, proof that the boundary shifts and wobbles, not fixed like a fence, but breathing like a tide. What lies beyond the heliopause is the true beginning of the space between stars. The interstellar medium, though incredibly thin, fills the galaxy. It holds the dust from ancient supernovae, the gas that forms new stars, and the electric and magnetic fields that twist through space. It is colder, denser, and more mysterious than the space inside our solar bubble. The heliopause is a frontier. It marks the end of the Sun's protection and the beginning of the galaxy's wide, wild openness. For the first time, we had sent machines across it. We had touched another part of space, not ruled by our star. The Voyager probes are billions of miles from Earth. Their signals take more than 16 hours to reach us. Their instruments are old, their power fading. But they are still speaking, still drifting, still sending whispers from the cosmic shoreline. The solar system's true size isn't what you think. When most people think about the solar system, they picture the 8 planets lined up neatly, orbiting the Sun. Beyond Neptune, it might seem like there's nothing else, just blackness. But that picture is far from complete. In truth, the solar system stretches far, far beyond the last known planet. And it doesn't just stretch in distance, it stretches in complexity. Much of the solar system's mass, mystery, and even structure is hidden in regions that can't be seen with the naked eye or even with ordinary telescopes. These outer zones are filled with icy bodies, drifting dust, and faint magnetic forces. They form the true edge of the solar system. Just past Neptune, about 30 times farther from the Sun than Earth, lies the Kuiper Belt. It's a ring of icy debris, like a second asteroid belt, but much larger and colder. This is where Pluto lives, along with other dwarf planets like Eris, Haumea, and Makemake. But those are just the biggest objects. The Kuiper Belt contains countless smaller bodies, frozen rocks, dirty snowballs, and fragments of the solar system's early days. The Kuiper Belt may look empty in pictures, but it holds more than we once thought. Some scientists believe there could be hundreds of thousands of icy objects wider than 100 kilometers. Others suggest there may be unseen forces tugging on these objects, possibly hinting at another distant planet, one not yet found. This idea, known as Planet 9, remains unconfirmed, but the strange orbits of some Kuiper Belt objects keep the mystery alive. Even farther out, well beyond the Kuiper Belt, lies a region we can't see at all. It's called the Oort cloud. Unlike the Kuiper Belt, which is shaped like a flat ring, the Oort cloud is believed to be a vast shell that surrounds the solar system in all directions. It could begin as close as 2,000 times Earth's distance from the Sun and stretch out to nearly 100,000 times that distance, or even more. That's a distance so large it takes light nearly 2 years to cross. The Oort cloud is the source of many of the long-period comets that appear suddenly in our skies, bright with tales and mystery. These comets are thought to have been nudged from their slow, distant orbits by the gravity of passing stars or galactic tides. When they fall inward, they give us a brief look at material that hasn't changed much since the solar system was born. No spacecraft has ever visited the Oort cloud. No telescope has seen it directly. Everything we know comes from observing how comets move when they enter the inner solar system. But if the Oort cloud is real, and most scientists believe it is, it could contain billions or even trillions of icy bodies. Some as small as mountains, others as large as worlds. Then there is the Sun's magnetic bubble. In many ways, the heliosphere is the outer wall of the solar system. But it's not the edge of the solar system in terms of material. That comes much farther out, where the Oort cloud may reach. So depending on how you define the edge, by magnetic influence, by orbiting objects, or by gravitational pull, the size of the solar system changes. Most of the solar system's size is made up of dark, cold regions we've never visited, and these regions may hold clues to our past. The Oort cloud, for example, may hold the same icy building blocks that formed the outer planets. Studying it, if we ever get close enough, could tell us what the early solar system looked like before planets formed. The Kuiper Belt, too, is a frozen fossil field. Its objects have likely changed very little over billions of years. They may contain organic molecules, water ice, and other ancient materials that hint at the conditions of the early Sun. Some of these distant regions may even hold rogue objects, things that didn't form here at all. It's possible that passing stars early in the solar system's history threw their own debris into our cloud, or maybe our Sun, once part of a dense star cluster, grabbed icy bodies from nearby systems. If so, the outer solar system may hold not only our history, but a shared history of other stars too. We often think of the planets as the center of the solar system's story. But the real bulk of the system, its volume, its mystery, its quietness, lies in the deep cold beyond. There are no spacecraft currently exploring these far regions directly. Only the Voyagers, drifting further every year, continue to report back from the edge. In time, new missions may be launched to the Kuiper Belt or beyond. Perhaps one day, we'll build a probe designed to reach the Oort cloud, or even to leave the solar system entirely and head toward another star. But for now, we rely on faint signals, comet trails, and distant calculations. The great cosmic speed limit, why we're practically standing still. A light year is how far light travels in a year, about 9.5 trillion kilometers. It's a number so big it loses all meaning unless you compare it to something closer to home. For example, it takes light just over a second to reach the Moon from Earth, about 8 minutes to reach us from the Sun. But the nearest star system, Alpha Centauri, is more than 4 light years away. Even at light speed, that's still a long trip. But here's the catch. We can't travel at light speed, not even close. According to Albert Einstein's theory of relativity, no object with mass can reach, let alone exceed, the speed of light in a vacuum, what scientists call c. As something with mass moves faster and faster, it becomes harder to push. It takes more and more energy. Near the speed of light, the energy needed grows so huge that it becomes infinite. And infinite energy isn't something we have, so instead we crawl. Take Voyager 1. It's moving at about 17 kilometers per second, roughly 61,000 kilometers per hour. That might sound fast on Earth, where even passenger jets only travel at about 900 kilometers per hour. But in the context of the cosmos, Voyager 1 is barely moving. It would take over 70,000 years for it to reach Proxima Centauri, the nearest star. Voyager wasn't trying to go fast. It just got a boost from the gravity of Jupiter and Saturn. We've built faster probes since then. The Parker Solar Probe, for instance, has reached speeds of over 190 kilometers per second as it loops closer and closer to the Sun. That's about 690,000 kilometers per hour, faster than any other human-made object. But even at that speed, reaching the nearest star would take over 6,000 years. If we wanted to reach just 1% the speed of light, around 3,000 kilometers per second, it would still take over 400 years to get to Proxima Centauri. And that's if we could accelerate to that speed in the first place, which we currently cannot. Why is it so hard? Part of the reason is energy. Speed and energy are linked. The faster you want to go, the more energy you need. But energy isn't just about fuel. It's about how you carry that fuel, how you burn it, and what your engine is capable of doing. Rockets, as they are today, are extremely inefficient when it comes to high-speed travel. They carry their own propellant, and the more fuel you add, the heavier the rocket becomes. That means you need more fuel to push that fuel, and then more to push that too. It's a vicious cycle that adds weight, but doesn't help much with speed. This is why spacecraft burn most of their fuel just getting off Earth. Once in space, they coast, using little or no power. That's great for orbital missions or visits to nearby planets, but it doesn't help if you want to cross trillions of kilometers. The other big problem is patience. Humans aren't built for journeys that take centuries. Our lives are short compared to the time it takes to reach another star at even a tiny fraction of light speed. If we launched a ship today that could travel at 0.01% of the speed of light, it would still take more than 40,000 years to get to Alpha Centauri. That's older than written human history. And yet, in theory, going faster is possible. If we could build engines that don't rely on traditional fuel, we might make it happen. Some scientists and engineers are already dreaming of spacecraft pushed by giant lasers or sunlight-catching sails. These ideas are still in their early stages, but they suggest we might someday reach 10%, maybe even 20% of light speed. At 10% light speed, Alpha Centauri would be just a 40-year trip, still long, but suddenly within reach for a single human lifetime. But even then, traveling at a meaningful fraction of the speed of light brings new problems. Space isn't empty. It's full of tiny particles, dust, atoms, and even single molecules floating in the dark. At slow speeds, they don't matter much, but at relativistic speeds, meaning a good percentage of light speed, those tiny particles become bullets. A grain of sand could strike a fast-moving spacecraft with the force of a bomb. Protecting against that is a whole engineering challenge of its own. And then there's time itself. At high speeds, time starts to act differently. This is another part of Einstein's theory. From the point of view of someone on a fast-moving ship, time actually slows down. If you could somehow travel at near light speed, time on board would pass more slowly than for people on Earth. A year on the ship might mean 10 years pass on Earth. This is a real effect, proven by experiments with atomic clocks on fast-moving jets and satellites. It's just that, at the low speeds we use today, the effect is too tiny to notice. But at relativistic speeds, it matters. A fast trip to another star might only take a few years for the travelers on board, even if decades pass back home. That's a strange idea to think about, and it brings up hard questions about what it means to explore space if we're not doing it in real time. Back on Earth, light speed still feels like an unreachable wall. It's not just a number, it's a cosmic rule, a speed limit that shapes everything we do in space. It keeps our messages delayed, our probes crawling, and our dreams of visiting other stars locked in long time scales. And yet, it also defines the shape of the universe. The reason we can see distant galaxies is because light from them has taken billions of years to reach us. If light traveled faster, or if we could travel faster, our picture of space and our place in it would be completely different. For now, our best bet is to keep pushing the limits slowly. Smarter engines, lighter spacecraft, better energy systems. We might not break the speed of light, but we can close the gap bit by bit. Maybe not in decades, but in centuries. And maybe, someday, a probe will leave Earth and reach another star. It might not carry humans, and it might not return, but it will mark a crossing of a barrier more real than any border or wall. It will mean we moved, however slowly, into the deeper galaxy. Until then, we remain, by cosmic standards, almost still. Voyager's long goodbye, the first embers of interstellar flight. Voyager 1 and Voyager 2 were launched during a special window in our solar system's alignment, an event that only comes around once every 176 years. The planets were lined up just right, allowing a spacecraft to use their gravity like a slingshot, gaining speed at each pass and swinging onward with hardly any extra fuel. It was a chance too good to miss, and so NASA sent out 2 spacecraft that would end up becoming the longest operating space missions in history. Voyager 2 launched first on August 20th, 1977. Voyager 1 followed a few weeks later on September 5th. Though it was launched later, Voyager 1 took a faster route and overtook its twin in just a matter of months. Each spacecraft carried a set of instruments, cameras, and detectors meant to study the planets, their moons, and the surrounding environment. And strapped to the side of both crafts was something unusual. A golden record. Etched into it were sounds and images from Earth. A message to any being who might find the spacecraft in the far future or in another corner of the galaxy. In their early years, both probes performed missions that were unmatched. Voyager 1 flew by Jupiter in 1979 and then Saturn in 1980. It sent back stunning photos of Jupiter's storms and volcanoes erupting on its moon, Io, something no one had ever seen before. At Saturn, it showed us new details of its rings and passed closely by the mysterious moon Titan. That encounter sent Voyager 1 on a new path, up and out of the solar system, away from the plane where most of the planets orbit. Voyager 2 had a different journey. After Jupiter in 1979 and Saturn in 1981, it continued to Uranus in 1986 and Neptune in 1989. No other spacecraft has visited those 2 outer planets since. Voyager 2 discovered new moons, mapped magnetic fields, and showed us what these icy worlds look like up close. At Neptune, it passed within just 5,000 kilometers of the cloud tops, closer than it came to any other planet. These flybys gave the probe speed. Jupiter's gravity sped up Voyager 1 and aimed it at Saturn. Saturn's gravity then launched it toward interstellar space. Voyager 2 used a similar trick, but in more steps. Each time, gravity from a giant planet bent the probe's path and added energy to its flight. No rocket could have done the same with the limited fuel on board. Gravity was the engine that made their long journey possible. After they finished visiting the planets, both Voyagers kept going. No longer tourists in the solar system, they became scouts. Even though they are now decades old, both probes are still talking to us. Their signals are weak, but they still send data. They don't have working cameras anymore. Those were shut down long ago to save power. But their remaining instruments give us a sense of what it's like out there, on the edge of the sun's domain. Even now, they continue drifting outward. They aren't going to any particular destination. There's nothing out there waiting for them, just more space. In about 300 years, they'll reach the inner edge of the Oort cloud. In 30,000 years, they might leave the Oort cloud entirely. And then they'll keep going, falling through the galaxy like cosmic bottles thrown into an endless ocean. They are incredible achievements, tiny machines, built with 1970s technology, still operating billions of kilometers away. But they also show how little we've moved the needle when it comes to real interstellar travel. In nearly 50 years, we haven't built anything that can catch up to them. No other spacecraft has matched their distance. Their technology is outdated, their computers primitive by today's standards. Each carries only about 68 kilobytes of memory, less than a single digital photo, and yet they remain the farthest. We've learned so much from them, but they've also highlighted the gap between dreams and reality. Interstellar flight takes power, precision, time, and technology that we're only starting to imagine. The Voyagers didn't solve those challenges. They bypassed them by staying small, unmanned, and slow. They showed us what could be done with patience and smart planning, but not how to send people or even fast probes beyond the solar system. As of now, both probes are slowly running out of power. Their radioisotope generators are decaying, producing less heat and electricity each year. To keep them going, engineers have been shutting down instruments one by one. Eventually, sometime in the 2030s, both Voyagers will fall silent. They'll go dark, still drifting, still intact, but no longer sending anything home. They'll keep flying, though. Long after Earth changes, long after their signals fade from our skies, they'll be out there, tracing lonely paths between the stars. In a way, they're our messengers, our fingerprints left on the void. The tyranny of Delta V. Why leaving is harder than landing. If you want to leave Earth, really leave it. Not just hover in orbit, not just fly past the moon, but actually break free and head for deep space. You have to pay a toll. Not in money, not in time, but in energy. Space is not a place you simply drift into. It demands force, speed, and planning, and above all, it demands Delta V. Delta V means change in velocity. In spaceflight, it's a measure of how much maneuvering a spacecraft can do. Think of it like a fuel budget. Every time a spacecraft fires its engines to speed up, slow down, turn, or change course, it spends some of that budget. The more Delta V you have, the more you can do. The less you have, the more limited you are. The problem is, space is huge, and it's full of gravity. Climbing out of Earth's gravity well, the deep pocket of pull that our planet holds, is one of the most energy-hungry parts of any mission. Even reaching low Earth orbit just 300 kilometers up takes about 9.3 to 10 kilometers per second of Delta V. That's almost everything most rockets can offer. It means by the time you're in orbit, you've already spent most of your energy just getting off the ground. After that, leaving Earth orbit to go somewhere else, like Mars, Jupiter, or beyond, requires even more Delta V. Not because you're climbing straight out of Earth's grasp, but because you need to pick up speed relative to the Sun. Earth is already moving around the Sun at nearly 30 kilometers per second. To escape the Sun completely, you'd have to increase that speed past 42 kilometers per second. That takes more fuel, which means more weight, which requires even more fuel, and so on. This is why interplanetary missions are often built around tight windows and gravity assists. You can't just point and shoot a probe wherever you want, whenever you want. Instead, You wait until the planets line up just right so you can take the most efficient path, called a transfer orbit. That timing might come only once every few years, and even then, the spacecraft has to be extremely light and efficient. To save fuel, missions often steal energy from planets. The spacecraft flies close to a planet, and as it swings around, the planet's gravity pulls on it, flinging it faster in a new direction. It's like using the mass of a moving truck to push a bicycle without touching it. The move is free in terms of fuel, but requires precise timing and distance. Even so, each little push from a planet is carefully planned. A small mistake in angle or timing can cost a lot of delta V to correct. In deep space, course changes are not cheap. The farther you are from your starting point, the more expensive they become. If you make a 1-degree error in a spacecraft's heading early in the flight, fixing it later might require tens or even hundreds of kilograms of fuel. That's why trajectory planning is one of the most critical parts of mission design, and it's why rockets are mostly fuel. A typical rocket might carry only 2–5% of its mass as payload. The rest is fuel and the tanks to hold it. The Saturn V, which sent astronauts to the moon, stood 110 meters tall. But the spacecraft on top, the command module, was the size of a small truck. All the rest was fuel burned in just a few minutes to get that tiny piece up and out of Earth's gravity. The deeper into space you go, the harder this problem becomes. A spacecraft going to Mars can coast much of the way once it's on course, but if you're aiming for interstellar space, you'll need much more energy and more delta V. And you can't count on planetary assists forever. Once you pass Neptune, there's nothing large left to help you. You're on your own. That's when the tyranny of delta V really takes hold. You can't simply add more fuel to solve the problem. The return on investment drops fast. It's like trying to climb a mountain by carrying a taller ladder on your back. The higher you want to go, the more the ladder weighs until it becomes impossible to lift at all. This is known as the rocket equation, and it's a constant challenge. Every gain in velocity comes at a cost. Exponential, not linear. Doubling your speed doesn't just double your fuel. It might quadruple it or more. The math is unforgiving. This is why so many space missions are slow. Not because engineers don't want to go faster, but because the cost of speed is brutal. Voyager 1 took 35 years to reach the heliopause. New Horizons took 9 years just to reach Pluto, and that was with a gravity assist from Jupiter. Our fastest spacecraft, the Parker Solar Probe, is only moving quickly because it's falling into the Sun, not escaping it. To truly leave the solar system in a reasonable time, a future spacecraft would need to go much faster than anything today. But to get there with rockets would require impossible amounts of fuel. So engineers are dreaming of other ways: solar sails, nuclear propulsion, or fusion drives. These ideas might one day break the grip of delta V, but for now, they remain only ideas. Even landing on other worlds is easier in some ways than escaping from them. If you have an atmosphere, like Mars or Earth, you can use it to slow down. Heat shields and parachutes do the work for you. But to leave, you need engines. You need fuel. You have to push against gravity all over again. That's why astronauts on the moon in the Apollo program didn't bring the whole spacecraft back. The lower half of the lunar lander stayed behind, used once and discarded. The upper half launched back into orbit with just enough fuel to get home. Every gram counted. This thinking extends to future missions. If we ever go to Mars, the mission may rely on making fuel there, extracting oxygen from the atmosphere, or breaking water into hydrogen and oxygen. Carrying all the fuel from Earth would be too heavy, too costly. Delta V is a ruler that limits what's possible. It decides where we can go, how long we can stay, and what we can bring. It shapes the entire architecture of space exploration. And until we find a way around it, it will continue to rule over our dreams of leaving not just Earth, but the solar system itself. Why no human has left low Earth orbit since 1972. In December 1972, Apollo 17 left the moon and came back home. No human has gone farther since. That mission, led by Eugene Cernan, marked the end of a bold, fast-paced era when humans were racing to the moon. It was also the end of the only time we've ever sent people beyond low Earth orbit. Since then, for more than 50 years, every astronaut has stayed within a tight bubble around our planet, barely a few hundred kilometers up. Why? At first glance, it seems strange. We have more advanced computers. We've launched probes to the edge of the solar system. Private companies send rockets to orbit multiple times a month. And yet, we haven't pushed people past low Earth orbit in half a century. The answer lies in a mix of cost, risk, and shifting goals. Sending humans far from Earth is hard, much harder than most people think. And the Apollo program, impressive as it was, never built the foundation for long-term spaceflight. It built a moment, not a bridge. After the moon landings, the United States turned its attention elsewhere. The Apollo program was expensive. By the early 1970s, the war in Vietnam, the economic strain at home, and changing political winds made it hard to keep funding missions that didn't seem urgent anymore. NASA had already met its goal, beat the Soviets to the moon. The big national challenge was done. There was no longer a clear reason to keep going. Plans to go to Mars or build permanent moon bases were shelved. The next big idea was the space shuttle. Instead of huge rockets that were used once and thrown away, the shuttle would be reusable. It would go up like a rocket and land like a plane. It would make space travel cheaper, safer, and more routine, or so people thought. In truth, the shuttle became a complex and expensive vehicle. It never reached the cost savings that had been hoped for, but it shaped NASA's direction for decades. The shuttle focused on building and supporting space stations in low Earth orbit, like Mir, and later the International Space Station. These missions helped scientists understand how the human body reacts to long-term space travel, how bones lose mass, how muscles weaken, how fluids shift in microgravity. But they also kept astronauts tethered close to Earth. The shuttle could only reach orbits around 300 to 600 kilometers up. Deep space was left to robotic explorers. And while the shuttles flew, the challenges of sending people farther never went away. Deep space means more than just more distance. It means a different kind of danger. Radiation becomes a major issue. Earth's magnetic field protects us from a lot of space radiation. But once you leave low Earth orbit, you're exposed to high-energy particles from the sun and deep space. Over days, weeks, or months, those particles can damage cells, increase cancer risks, or even trigger nervous system problems. Shielding against radiation is heavy and hard to design. Then there's life support. On the Moon, the longest stay was just a few days. But future missions, to Mars or even to a lunar base, will take weeks, months, or years. That means you need reliable air recycling, water recovery, food storage, and waste handling. The systems have to be almost perfect. A single failure could be fatal, and unlike the International Space Station, you can't rely on frequent supply runs. You're on your own. In low Earth orbit, if something goes wrong, you can be back on the ground in a few hours. But in deep space, rescue isn't an option. A mission to Mars, for example, would take months just to get there. If something breaks halfway, you can't turn around. The spacecraft has to be fully self-sufficient. The people on board need to solve problems without any outside help. That level of redundancy and safety comes at a huge cost. And then there's the rocket itself. The Saturn V rocket that launched Apollo was the most powerful rocket ever built. But it wasn't built to be reused. Each launch cost hundreds of millions of dollars. Rebuilding something like Saturn V from scratch would take years, and possibly tens of billions of dollars. For decades after Apollo, no one was willing to spend that money. Not because no one cared, but because the risks and rewards didn't line up. Space agencies turned to robotic missions instead. They were cheaper, safer, and could go farther. Voyager, Galileo, Cassini, Curiosity, all built by engineers and controlled from Earth. These probes taught us about the planets, the moons, the rings, the atmospheres. They didn't need oxygen, they didn't need food. And if something went wrong, no lives were lost. Some people see this as a lack of ambition, but the truth is, robotic spaceflight let us learn first. Before we send humans to Mars, we need to know what kind of soil they'll land on. Before we build a base on the Moon, we need to know where the ice is and how to use it. And even today, with all that knowledge, we're still figuring out how to keep people alive for long periods in space without relying on constant resupply. Now things are changing again. NASA has built a new rocket, the Space Launch System. Private companies like SpaceX are working on their own heavy launch systems. Plans are being made to return to the moon with Artemis. But even this is only the start of the long climb back toward deep space travel. These missions still face the same hard limits: radiation, fuel, life support, distance, time. The reason we haven't left low Earth orbit in so long isn't because we lost the dream. Every mission beyond Earth's protective bubble is a high-stakes journey into the unknown, and until we build systems that can handle all that risk, reliably, repeatedly, and affordably, we won't be traveling too far from home. Why are rockets max out so quickly? At the heart of every chemical rocket is a combustion chamber. This is where fuel and oxidizer mix and burn at high pressure, creating hot gases that blast out through a nozzle. That rushing gas creates thrust. But this process has limits. The pressure inside the chamber can't rise forever. The materials must survive extreme heat and stress. Push it too far and the chamber melts, cracks, or explodes. Engineers have worked for decades to raise these limits. Stronger alloys, better cooling, tighter tolerances. But even with all the advances, we're still stuck in a narrow range. Most modern chemical rockets operate at chamber pressures between 100 and 300 atmospheres. That's hundreds of times the pressure at sea level. But if you want more thrust, just making the pressure higher doesn't always work. The engine might overheat, the walls might not be thick enough, or the fuel might not burn cleanly. The materials can only take so much abuse. And then there's the nozzle. This is the bell-shaped exit that directs the exhaust and helps generate forward thrust. A well-designed nozzle can squeeze every bit of speed out of the gas. But here too, there are trade-offs. A nozzle that works well at sea level performs badly in space. One that's perfect for vacuum won't work on the launch pad. Engineers have to choose where the rocket will perform best. That's why most rockets have multiple stages, one optimized for thick air, one for the thin upper atmosphere, and one for space. Each stage sheds dead weight and gives the next a boost. Even with all these optimizations, we run into a deeper problem. The speed you can reach depends not just on how much fuel you have, but how fast your engine can push the fuel out. This is called exhaust velocity. Chemical rockets, even the best ones, top out at around 4 to 5 kilometers per second. Once you're out of fuel, you're done. That means that often more than 90% of the rocket's total weight is fuel. The early space programs ran into this over and over. Saturn V weighed more than 3,000 tons fully fueled, but the spacecraft at the very top, where the astronauts actually rode, weighed just a few dozen tons. Modern rockets aren't much better. Falcon Heavy, for all its upgrades, still follows the same basic rules. So does Artemis. So do nearly all launch systems in development today. They rely on chemical combustion. They rely on pushing burning gas out a nozzle, and because of that, their performance plateaus. You can only squeeze so much energy out of chemical bonds. The specific impulse, the measure of how efficient an engine is, caps out at around 450 seconds for the best liquid fuel engines. Most are less. To go faster, we need more than brute force. We need a better way to push. That's why engineers have looked at electric propulsion, ion drives, and even nuclear-powered systems. These methods don't burn fuel the same way. Instead of heat and pressure, they use electric fields or nuclear reactions to throw particles out at much higher speeds. Ion engines, for example, have exhaust velocities 10 times higher than chemical rockets. They're far more efficient. But there's a catch. They generate almost no thrust. They can't lift anything off the ground. They're only useful once you're already in space, and even then, they take weeks or months to build up speed. That's the trade-off we keep running into. High thrust comes with low efficiency. High efficiency comes with low thrust. There's no magic engine, at least not yet, that gives you both. And without that, every deep space mission ends up being a compromise. You launch with a huge chemical booster, coast through space using solar panels or low-thrust engines, and arrive late. Years late. That's why, for all our progress, interstellar travel still feels like a dream. Our rockets max out because they hit hard walls in physics. We can't push the gas any faster. We can't make the tanks any lighter. We can't pack in more energy without blowing the thing apart. And so, for now, we're left watching tiny metal craft drift through space, crawling past the outer edges of the sun's reach. Fuel, mass, and the exponential trap of rocket physics. Rockets are strange machines. They don't carry gas like a car does. They don't just refill and keep going. A rocket carries all its fuel at once, packed tight in tanks, and it doesn't push off against anything. It works by throwing stuff backward, burned fuel rushing out a nozzle, so the rocket moves forward. That's all a rocket is doing, pushing against its own fuel. If you want to go faster or farther or carry more, you can't just add more fuel. You hit a wall called the rocket equation. The rocket equation says that the delta V of a rocket depends on two things: how fast it can throw out its fuel and how much fuel it has compared to the mass of the rocket. Imagine you have a small rocket. Let's say the part of the rocket that isn't fuel, the payload and structure, has a mass of 1 ton. If you add 1 ton of fuel, you now have a total mass of 2 tons. That's a 1:2 ratio of dry mass to full mass. That's not bad. That rocket will get a certain speed boost, delta V, when the engine fires and throws that fuel out the back. But now let's say you want to go faster. You add another ton of fuel. Now your rocket weighs 3 tons, but that extra ton of fuel has to push not just the payload, but also the first ton of fuel. And if you want that second ton of fuel to be effective, it needs even more fuel to push it. So you add more, and it starts piling up. Let's take it a step further. Suppose you want to double the speed change, the delta V of your rocket. Just doubling doesn't mean doubling the fuel. You might need 5 or 10 times as much. At some point, your rocket is mostly fuel tanks and engines. The part you care about, the actual spacecraft, is tiny. You can keep adding fuel, but you get less and less return. That's the exponential trap. This isn't bad engineering. It's built into the physics. The rocket equation says that to gain each extra unit of speed, you must multiply the total mass of the rocket. You go up a little in delta V, and your fuel mass grows exponentially. That's why real rockets often look huge and mostly empty. We can also think about this using staging. A rocket like Saturn V dropped empty tanks along the way. Each stage peeled away after its job was done. By shedding mass, the rocket could gain speed more efficiently. But even with staging, the numbers are tough. The first stage lifted the second lifted the third. Only the final stage carried the payload, the Apollo capsule, into space. The rocket equation doesn't care if you're launching a moon lander or a probe to Pluto. It treats every plan the same. Suppose we want to build a small probe that weighs 500 kilograms. We want to give it a delta V of 9 kilometers per s, enough to escape Earth orbit and head towards deep space. Using standard chemical engines with an exhaust velocity of around 4.5 kilometers per s, the rocket equation tells us we need about 8 times the mass in fuel compared to the dry mass. That means 4,000 kilograms of fuel just to push 500 kilograms. That's not too bad. But suppose we want to go faster, say 12 kilometers per s. Now we need nearly 20 times the mass in fuel. That's 10,000 kilograms of fuel for the same 500 kilogram probe. And if we want 15 kilometers per s, suddenly it's over 50 times the dry mass. Now you're carrying 25 tons of fuel, and that's just to go a little faster. That's the trap. It doesn't take much to go from reasonable to ridiculous. Every extra kilometer per second costs more and more, and most of that fuel is just there to lift other fuel. It doesn't directly move your payload, it's just the price you pay to carry the rest. There are some ways to cheat the equation. You can build spacecraft in orbit, so you don't need to lift everything from the ground. You can use other forms of propulsion that have higher exhaust velocity and better efficiency. But even then, the gains are slow. The rocket equation still holds. it just stretches the curve a little farther. Radiation belts and human fragility in the interplanetary void. Space may look like a black void, but it's filled with invisible threats. Radiation is everywhere, coming from the sun, coming from distant stars, even coming from events that happened billions of years ago. These are high-energy particles moving at nearly the speed of light, and they are not kind to the human body. Our magnetic field wraps the planet in an invisible cocoon. That cocoon traps many of the charged particles that would otherwise slam into us. The trapped particles swirl around in two large regions called the Van Allen belts. These belts were discovered in the late 1950s, and they mark the first barrier any spacecraft must pass when leaving Earth. The inner belt is filled with protons, the outer belt with electrons. They are not deadly if you move through them quickly, but linger too long and the exposure builds up. Satellites can orbit below the belts or pass through them with protection, but they don't stay in the belts. For humans, even a few hours in that region requires planning. The Apollo missions had to cut through the Van Allen belts on their way to the Moon. They did it by choosing a path that crossed the thinnest parts of the belts, and they moved through quickly, less than an hour. That was enough to keep radiation exposure low. Once you leave Earth's magnetic bubble, you're exposed to deep space radiation. This radiation comes in two main forms: solar particles and galactic cosmic rays. Solar particles are not always present in high numbers, but during solar flares or coronal mass ejections, the Sun can hurl massive amounts of these particles across the solar system. When that happens, the flux of radiation spikes for hours or days. These solar storms can't always be predicted with much warning. For astronauts in space, a big solar event can be dangerous, even deadly, if they're not protected. On the International Space Station, the crew is still inside Earth's magnetic field. They have shielding. They can move to areas with extra protection. But on a long mission to Mars or deep space, there's no quick retreat. Some mission plans include a small shelter inside the ship, a thick-walled box made of plastic or water tanks where the crew can hide during a solar storm. But that adds mass. And mass is always a problem. Galactic cosmic rays are far worse. They come from outside the solar system, blasted into space by supernovas, neutron stars, black holes. These particles travel for millions of years and hit with extreme energy. They are fewer in number than solar particles, but far more powerful. They can rip through human cells, damaging DNA and raising cancer risk. They can penetrate most spacecraft walls. Shielding helps, but not much. To truly block cosmic rays, you'd need meters of thick material, like lead or water or dense plastic. That kind of shielding is just too heavy for most missions. Radiation in space is measured in units that reflect biological harm, such as sieverts. On Earth, people might be exposed to 2 or 3 millisieverts per year from natural background radiation. On a 6-month trip to Mars, astronauts might get 300 millisieverts or more. That's like having a full-body CT scan every few days. Over time, it increases the risk of cancer. It also weakens the immune system, damages the brain, and may even speed up aging. Robotic probes don't care about radiation. Their electronics can be hardened. They don't get cancer. They don't get sick. They just work, or they fail. And even if they fail, we just build another. But humans are different. Our bodies rely on stable environments. Our cells divide and repair. Our organs are sensitive to damage, and we only get one body. We can't send up a spare. Designing a spacecraft for humans means making trade-offs. More shielding adds safety, but it also adds weight, and weight means more fuel. And more fuel means bigger rockets, longer launch windows, and more cost. Some materials work better than others. Metals like aluminum stop some radiation, but also generate secondary particles when hit. Plastics work better in some cases. Water is good at slowing down charged particles. That's why some concepts use water tanks or food stores as makeshift shields. Space agencies test materials in labs. They simulate radiation with particle accelerators. They model how different ship designs might protect a crew. But simulations only go so far. No one has sent humans on a years-long mission beyond Earth's magnetic field. no one knows what the long-term effects will be. The longest any human has spent in space was just over a year. That was aboard the International Space Station. They were still under the protective cover of Earth's magnetosphere. Going to Mars would mean a round trip of about 2 to 3 years. That's far more exposure. And once you're on Mars, you're standing on a planet with no magnetic field and only a thin atmosphere. You're still getting hit by cosmic rays. Some suggest timing missions during solar maximum, when the sun is most active. That might seem strange, but during solar maximum, the increased solar wind helps push back galactic cosmic rays. You get more solar radiation, but less from outside the solar system. It's a trade-off. Others suggest building habitats underground, using Martian soil as natural shielding. That might work for a base, but not for the journey to get there. The fragility of the human body is a central limit in space travel. Machines can go faster, farther, and withstand harsher conditions. But if we want to send people, really send them, we have to solve the radiation problem. That means better materials, smarter ship design, or new kinds of propulsion that get us to our destination faster, cutting down the exposure time. Right now, every extra day in space is another day we're exposed to something that was never meant for us. Project Orion, the spaceship that rode the bomb. There was a moment in the late 1950s and early 1960s when engineers thought they had found a shortcut to the stars. They called it Project Orion. The idea was simple, almost brutal. If chemical rockets weren't strong enough to push a spaceship fast enough for real interstellar travel, then use something that was. Use bombs. Nuclear bombs. At its core, Project Orion was a plan to build a spacecraft that would ride a series of nuclear explosions into space. The basic design had a strong, flat pusher plate at the back of the ship. Just ahead of the plate was a set of shock absorbers, giant mechanical springs. Behind the ship, small nuclear bombs would be released, one after another, and detonated at just the right distance. Each explosion would slam into the plate with a tremendous shockwave, and the shock absorbers would soften the blow, turning each blast into forward motion. Real scientists and engineers, many of them serious and respected, worked on the project. The idea started in 1958 under the guidance of physicist Freeman Dyson, engineer Ted Taylor, and others. They were trying to break free from the limits that chemical propulsion had placed on spaceflight from the very beginning. The numbers were stunning. A properly designed Orion ship, powered by hundreds or thousands of small nuclear bombs, could reach speeds that chemical rockets couldn't dream of. Some designs aimed for 3% to 5% the speed of light. Others pushed for 10%. That kind of speed would make interstellar travel at least thinkable. A journey to another star system might still take decades, but not centuries. The key was specific impulse, a measure of how much thrust you get per unit of fuel. Chemical rockets have a specific impulse in the hundreds of seconds. Nuclear thermal rockets might push into the low thousands. Orion promised specific impulses of tens of thousands of seconds. It was an enormous jump. Not only that, but it scaled well. A bigger Orion ship could carry more bombs, which gave more thrust. It could carry more mass, more shielding, more crew, more supplies. It was the kind of system that worked better the larger it got. There were even blueprints for giant Orion craft. One version, known as the Super Orion, was a monster, possibly 4,000 tons in mass, powered by hydrogen bombs, capable of carrying people to Saturn in months or to nearby stars in decades. Dyson once said that if humanity ever built something that could reach Alpha Centauri within a human lifetime, it would look like an Orion. Tests were done. Not full-scale nuclear tests, but small experiments. Engineers used chemical explosives to test how the shockwave would push against a pusher plate. They modeled how the plate would hold up, how the shocks would transmit through the structure. They figured out how often to detonate the bombs, perhaps one every second or two. They worked on methods to eject the bombs backward at precise intervals. It wasn't easy, but it wasn't impossible. And then, the whole idea ran into a wall. By the early 1960s, The world had begun to understand the dangers of nuclear testing. Fallout from above-ground explosions was drifting across countries and oceans. People were worried about radiation, cancers, and the long-term health effects of nuclear weapons. In 1963, the United States, the Soviet Union, and the United Kingdom signed the Partial Test Ban Treaty. It banned nuclear explosions in the atmosphere, underwater, and in space. That meant the heart of Orion, its string of nuclear detonations, was illegal. There was no easy way around it. To test Orion for real, they would have had to violate the treaty or test it in secret. Neither option was acceptable. The project had military backing in the early days, but even the military became uneasy. The idea of a spaceship flinging bombs into space, where they might explode near Earth or other satellites, was too risky. Eventually, the funding stopped. The engineers moved on. Project Orion faded into history, but the idea never quite died. The promise of nuclear pulse propulsion still lingers in some corners of space research. In theory, it works. Nothing in the laws of physics says it can't. It just collides hard with the realities of politics, safety, and public fear. Even if the treaties were changed, there would still be challenges. Each nuclear pulse would create a flash of high-energy particles, which could damage the ship or nearby electronics. The shockwave might be hard to control. The long chain of perfectly timed explosions would require extreme precision. And the bombs themselves, each a miniature nuclear device, would raise questions about storage, arming, and accidental detonation. Still, Orion showed that there is a way, in theory, to build a ship that could leave the solar system within a human lifetime. It doesn't rely on slow chemical rockets or electric thrusters that take years to build speed. It relies on raw power, brutal, unfiltered energy. Some have suggested modern alternatives. Maybe Orion could use fusion bombs instead of fission. Maybe we could build it in space, far from Earth, and launch it from there. Others propose designs like Medusa, where a giant sail catches the blast instead of a solid plate, which might reduce stress on the structure. These are just sketches for now. No nation is seriously building them. But the lesson of Orion is still important. It shows how big the gap is between what we want and what we can build. We want to reach the stars, but our tools are weak. Orion offered something that felt real, if only for a moment. A machine that didn't crawl through space. It charged, carried by a thunderous rhythm of artificial suns. The political fallout from the 20th century shut the door on Orion, and perhaps rightly so. But behind that door is still the only known propulsion system that could, with current knowledge and materials, take a human being to another star. The ghost of Project Daedalus, when engineers dared to think big. In the 1970s, a small group of engineers and scientists in Britain decided to think bigger than anyone else dared. They were part of the British Interplanetary Society, an old institution with deep roots in rocketry and spaceflight history. They had no rockets, no labs, no national funding. What they had was time, calculators, and an idea that reached across light years. They called their project Daedalus. Where most spacecraft designs stayed close to Earth, or at most the Moon, and where even the boldest plans for Mars seemed risky, Project Daedalus aimed for something far beyond. It was a proposal for an unmanned probe that would travel to another star system. Specifically, to Barnard's star, a red dwarf located about 6 light-years from Earth. It was the second closest star system we knew at the time, and for a while, there was even a suspicion that it had a planet. The engineers weren't designing something that could fly with the tools of the 1970s. Their goal was to see if interstellar travel was possible, using technology that was just barely within reach. They assumed humanity would eventually master certain advanced systems, and they used those as the basis for their design. The result was one of the most detailed, serious attempts to work out a plan for a real interstellar spacecraft. The Daedalus ship was enormous. It would be over 190 meters long. It would weigh 54,000 tons at launch, most of that fuel. It wouldn't use chemical rockets or nuclear fission, like Project Orion. Instead, it would run on nuclear fusion, the same reaction that powers the sun. The idea was to use pellets made of deuterium and helium-3, compressed by powerful electron beams to trigger tiny fusion explosions. Each explosion would create a burst of energy directed by a magnetic nozzle to produce thrust. Unlike Orion, Daedalus didn't need a series of actual bombs. It was more refined, but it was also more fragile. Fusion is hard to control. It requires perfect timing, enormous energy, and careful balance. And helium-3, one of the two fuels required, is incredibly rare on Earth. The team assumed it would have to be mined from the atmospheres of Jupiter or other gas giants. Daedalus was designed as a two-stage spacecraft. The first stage would fire for just over 2 years, accelerating the probe to about 7% the speed of light. Once the fuel ran out, the first stage would detach and the second stage would ignite for a little over a year more, boosting the ship to its final cruising speed, roughly 12% the speed of light. At that rate, the ship would reach Barnard's star in about 50 years. But it was a one-way trip, and it was uncrewed. There was no plan for the ship to stop, no method for slowing down. Once launched, it would speed through space for decades, take pictures and readings as it passed its target system, and then vanish into the dark. There would be no recovery, just a brief window of data sent home across light years, and then silence. In many ways, Project Daedalus was the opposite of Orion. Orion was blunt, heavy, and designed to carry people. Daedalus was sleek, fast, and robotic. Orion relied on brute force. Daedalus tried to ride something more elegant, controlled fusion reactions, each one releasing energy in a carefully guided direction. Neither ship was ever built. They remain engineering studies, detailed, thoughtful, and daring, but still only ideas. Part of the reason is cost. A Daedalus mission would be enormous, not just in size, but in money and time. It would need fusion reactors, helium-3 mining operations, precision manufacturing of pellet fuel, and deep space communication systems that could send signals home from 6 light-years away. Another reason is that we still don't have working fusion power on Earth, let alone in a spacecraft. Fusion has been a promise for decades, but controlled, sustained fusion has never been easy. Every lab that's tried it runs into the same problems: keeping the reaction going, managing the heat, handling the materials, and making it efficient. If we can't do it in a power plant, doing it in a spaceship flying at a fraction of light speed is even harder. If Daedalus succeeded, it would send back a few years of data, at best. A snapshot of a foreign star system, a brief message from a probe that no one could ever touch again. In an age where budgets are tight and people want quick results, it's hard to convince a government or even a private company to fund something that might not pay off for half a century. But Daedalus set a benchmark. In later years, the same group returned with a new design, Project Icarus, a modern version of Daedalus, using newer materials and updated models. Other groups have picked up the torch too. Concepts like Breakthrough Starshot aim to send tiny laser-driven probes to Alpha Centauri at a significant fraction of light speed, though with different technologies and goals. But Daedalus still stands as one of the clearest roadmaps we have to real starflight. It imagined a ship built in space, lit by fusion, gliding at tremendous speed across the gap between stars. Not to colonize, just to go, to see, to know. Why nuclear thermal propulsion remains a political no-fly zone. Nuclear thermal propulsion has been studied since the early days of the space race. The basic concept is simple. Take a nuclear reactor, pump liquid hydrogen through it, heat that hydrogen to thousands of degrees, and shoot it out the back of a rocket nozzle. The superheated gas expands rapidly, creating thrust. Unlike chemical rockets, which rely on chemical reactions to release energy, nuclear thermal engines use nuclear fission to generate intense heat, which is then transferred directly to the fuel. This setup produces a much higher specific impulse. With nuclear thermal propulsion, or NTP, a spacecraft could get nearly twice the performance of a traditional chemical rocket. That means either going much faster, carrying much more weight, or reaching a destination with more fuel in reserve. For missions beyond Earth orbit, especially to Mars or the outer solar system, that extra efficiency could make a huge difference. You could shorten trip times and still arrive with enough supplies for a real mission. Unlike chemical rockets, NTP doesn't need to carry heavy oxidizers. And unlike more futuristic ideas like fusion propulsion or antimatter drives, nuclear thermal engines have already been built and tested. In the 1960s and 70s, under programs like NASA's NERVA, or Nuclear Engine for Rocket Vehicle Application, full-scale NTP engines were fired on the ground in Nevada. They worked. They ran hot and clean, and they matched or exceeded their design goals. Engineers learned how to handle the heat, how to build the reactors, and how to protect the systems. On paper, we were ready for deep space travel. But the tests stopped. The political tide turned, funding dried up, and even now, decades later, nuclear thermal propulsion remains stuck in place. Nuclear anything carries a heavy burden. The idea of launching a rocket with a live nuclear reactor on board, especially from Earth, triggers deep fears. Accidents, even rare ones, loom large in people's minds. A single launch failure could spread radioactive material across a wide area. No matter how many safety systems are built in, the risk feels personal in a way that other technologies don't. Even though chemical rockets have exploded on launch pads many times, and even though satellites already carry radioactive sources for power, the idea of lighting up a nuclear reactor in our atmosphere still feels like crossing a line. Another challenge comes from international treaties. The Outer Space Treaty of 1967, along with other agreements, sets limits on what kinds of nuclear materials can be used in space. While these laws don't ban nuclear propulsion outright, they require careful review, strict controls, and international cooperation. In a world where space is becoming more crowded and more contested, these legal hurdles are growing, not shrinking. Countries are wary of each other's motives. A nuclear spacecraft might be for Mars, or it might look like a weapon. And that ambiguity makes everyone nervous. There's also the matter of cost. Building a nuclear rocket engine isn't cheap. It involves highly enriched uranium, radiation shielding, and specialized manufacturing. All of it has to be handled under strict oversight. Test facilities must be remote, secure, and equipped to handle the risks. There are few places in the world that can do this work, and fewer still with the political will to fund it. Compared to the relative ease of chemical propulsion or even solar electric drives, NTP remains a high bar. And yet the benefits are clear. A nuclear thermal engine doesn't need exotic fuels or breakthrough science. It's just heat and hydrogen. The designs are robust, the thrust is steady and high enough to lift real payloads. For a mission to Mars, NTP could cut the round-trip time by several months. For human spaceflight, it's a huge improvement. NASA hasn't given up on the idea. In recent years, the agency has restarted NTP research under its Space Nuclear Propulsion Program. There's collaboration with the Department of Energy. There are new materials, new fuels, and new safety systems. Some designs use low-enriched uranium to reduce proliferation risks. Some use modern reactors with better control and higher burn-up rates. Engineers are applying decades of advances from terrestrial nuclear power to make these engines lighter, safer, and more effective. Private companies are getting involved too. Some startups and contractors are exploring compact nuclear designs for deep space missions. They see a market for cargo tugs, interplanetary transport, and even moon bases supported by nuclear-powered shuttles. But even here, the progress is slow. The regulatory burden is heavy. The testing options are limited, and every step forward has to be justified to politicians, the public, and the international community. The truth is, we have a tool that could make spaceflight vastly more capable. And we're choosing not to use it because we haven't figured out how to manage the risks, real and perceived. We're held back not by science, but by trust. Trust in the technology, trust in each other, and trust in our ability to launch something powerful without turning it into something dangerous. If nuclear thermal propulsion ever gets its chance, it could make real exploration of the solar system possible, not just for robots, but for people. It could be the bridge between what we dream about and what we can actually do. But until we resolve the fears, the laws, and the costs, it remains grounded, a powerful idea with nowhere to go. The human hibernation question, science or speculation? If we can't cross interstellar distances in a reasonable number of years, maybe we can just skip them, sleep through them. That's the idea behind human hibernation. Or more precisely, the idea of placing astronauts in a state of long-term controlled inactivity, where the body's needs slow down, metabolism drops, and time passes quietly. In the animal world, hibernation is real and well understood. Bears do it. Squirrels do it. Even certain birds and reptiles go into a kind of deep sleep when conditions become harsh. In these states, body temperature lowers, breathing slows, and the animal lives off stored fat. Heart rates can drop to just a few beats per minute. In some small mammals, core body temperature falls to just above freezing. These creatures survive for weeks or even months this way, only to wake up later and resume normal life. Humans don't have a natural hibernation mode, but researchers are exploring ways to mimic it, often using studies of animals as guides. One focus is on a condition called torpor. In biology, torpor refers to a temporary state of reduced activity and metabolism. It's like a short-term version of hibernation. Some animals enter torpor nightly, others seasonally. Scientists believe that if we could safely induce a torpor-like state in humans, we might be able to greatly reduce the physical demands of long space missions. There's some progress in the lab. Doctors already use certain techniques that resemble parts of this process. For example, therapeutic hypothermia is used in medicine during surgeries or after cardiac arrest. By cooling the body, doctors can slow down brain activity and reduce the risk of damage when oxygen supply is low. Patients can be kept in a low-temperature state for hours or even a day or two. Their bodies slow down, and their energy use drops. But it's not hibernation. It's a carefully managed emergency response. Real hibernation would need to last much longer, months or even years. No one has ever managed to put a healthy human into long-duration torpor. The risks are many. Muscles and bones start to weaken quickly when unused. Blood flow becomes harder to manage. Internal organs need constant regulation. Even turning the patient regularly to prevent pressure sores becomes a challenge. A sleeping person still needs food, water, oxygen, and waste removal. These needs don't disappear, they just slow down. One path researchers are exploring involves pharmacology. Certain drugs can mimic the effects of torpor in animals, and scientists are testing whether similar compounds might work in humans. In some studies, hydrogen sulfide, a gas that can reduce oxygen use, has shown promise in inducing a low metabolism state in mice. Other compounds affect neurotransmitters tied to sleep and metabolism. But so far, no drug or combination has been able to create stable, long-term torpor in people. The results are early, small, and uncertain. There's also the idea of using specialized chambers, environments where temperature, oxygen, and pressure can be controlled to guide the body into and out of a suspended state. These setups would look like advanced medical beds, complete with monitors, feeding tubes, and robotic systems to handle care. The goal would be to keep astronauts alive with minimal activity for long voyages. They wouldn't be unconscious in the usual way, but rather deeply suppressed, slowed to a crawl in every function. Their brains would remain intact, but inactive. Their hearts would keep beating, just more slowly. Their bodies would use less fuel, produce less waste, and need less space. It's a delicate balance. Go too far, and you risk organ failure. Don't go far enough, and the benefits disappear. Managing body temperature, especially in space, introduces more problems. Cooling the human body safely requires not just dropping external temperature, but ensuring the core cools evenly and doesn't trigger shock. In animals that hibernate, this process happens gradually, guided by natural biology. In humans, it has to be controlled minute by minute, with technology watching every change. And even if we solve the biological part, there are practical issues too. Weightlessness causes muscle atrophy and bone thinning. If astronauts are in torpor, they won't be exercising, which worsens the problem. Fluid shifts in the body also increase the risk of blood clots and eye problems. In torpor, those fluids may pool dangerously. Countermeasures, like compression suits or artificial gravity, would have to work even during hibernation. In animals, waking from hibernation takes time. They shiver, they move slowly, their organs warm up over hours. For humans, rewarming a cold body without harm is tricky. It would require heating systems, nutrient delivery, and constant medical checks. If something goes wrong mid-voyage and the systems can't revive a crew member, or worse, the whole crew, the mission could be lost. So even if hibernation works, fail-safes and redundancy will be critical. This concept is very different from cryogenic freezing. Cryonics, the idea of freezing a human completely. When water freezes, it forms ice crystals, which destroy cells. Some labs use chemicals called cryoprotectants to prevent this, but these substances are toxic in large amounts. So far, no mammal has been frozen solid and revived. Some frogs and insects can survive being frozen, but they have evolved special proteins and behaviors to manage the damage. Humans haven't. Torpor is also different from artificial sleep or anesthesia. In those states, the brain is quieted, but the metabolism keeps running at near normal rates. You still need normal amounts of oxygen, water, and nutrients. The body ages, muscles waste, and after weeks or months in a coma, people need long rehabilitation. True torpor would be more like hitting pause on all activity. So where does that leave us? Torpor is not impossible. The biology exists in nature. The technology, at least in part, already surrounds us in modern medicine. What's missing is a reliable long-term method to apply it to humans in space. No one doubts that it would be a game changer. For missions to Mars or the outer planets, it could reduce food loads, water needs, and psychological stress. For missions beyond the solar system, it might be the only way to make travel possible at all. But right now, it's not ready. The studies continue. Science fiction keeps imagining crews sleeping through centuries. But the body, for now, keeps asking for something simpler. To eat, to breathe, to move, to be awake. How long would it really take to reach Alpha Centauri with current tech? Alpha Centauri is the star closest to us, at just over 4 light-years away. 4 light-years is about 25 trillion miles. That's 160,000 times farther than the distance from Earth to the Sun. With the spacecraft we have today, it would take tens of thousands of years to get there. That's the problem with chemical rockets. They give you a big kick at the start, but then run out of gas immediately. Even if we launched a mission specifically to Alpha Centauri using our best rockets and optimized every detail, the best-case scenario, still chemical, would be a journey lasting many millennia. That leads to other ideas. One of the most promising is solar sailing. A solar sail works more like a boat than a rocket. It has a large, thin reflective surface which catches photons from the sun. Photons have no mass, but they do carry momentum. Over time, this pressure builds up. Slowly but steadily, a solar sail accelerates. There's no fuel. The sun's light does all the work. If you can build a sail big enough and light enough, and if you can point it properly, it can reach speeds chemical rockets never could. Missions like the Japanese Icaros spacecraft have proven that the idea works in principle. But to really make it useful for interstellar travel, you'd have to scale it up dramatically. Think of a sail the size of a football field, or larger. Then, reduce the mass of the payload to something smaller than a shoebox. The more sail and the less weight, the faster you go. There's also the concept of using lasers from Earth to push these sails, rather than just relying on sunlight. That's the idea behind Breakthrough Starshot, a private initiative that wants to send tiny spacecraft, just grams in size, to Alpha Centauri. The plan is to use powerful ground-based lasers to push a sail to speeds up to 20% the speed of light. At that speed, the trip would take just over 20 years. But that's theory. No such laser array exists yet. And there are massive technical challenges, from guiding the laser over millions of miles to making sure the sail doesn't rip apart during acceleration. Even if the system works, the payload will be extremely limited, just a chip-sized camera and a power supply. There's no way to send people or even a traditional robotic lander. More realistic solar sails, built with current materials and pushed only by the sun, wouldn't reach those speeds. The best projections suggest they could reach a few hundred kilometers per second. That's much faster than chemical rockets, but still only a fraction of a percent of the speed of light. That means travel times to Alpha Centauri would drop from 70,000 years to maybe 5,000 or 10,000. That's a huge improvement, but it's still far beyond a human lifetime. It means a mission that would span dozens or hundreds of generations. Even with the best of today's technology, a trip to another star is not a trip for people. It's a mission you'd launch knowing that nobody alive now would ever see the result. The spacecraft would have to operate on its own for thousands of years, powered by tiny nuclear batteries or some unknown future source. Its software would need to survive glitches, radiation, and cosmic dust. Its antennas would need to aim perfectly back at Earth across trillions of miles to send back a signal. And Earth itself would have to be listening, maybe centuries from now. There's a temptation to think in terms of speed records. Couldn't we just build a faster engine? Couldn't we just put more fuel on the rocket? But the numbers don't work that way. That's why radical ideas like fusion or antimatter drives get proposed. Because without a completely new kind of propulsion, we're stuck with slow. If it takes 10,000 years to reach the nearest star, then any mission is either robotic or generational. Either we send machines that last longer than civilizations, or we send people who live and die along the way, passing down the mission through their children. Generational starships are a familiar idea in fiction, but in reality, they're far more complex. How do you build a closed life support system that lasts centuries? How do you deal with politics, psychology, education, and medicine in a sealed, artificial world? So when we ask how long it would really take to get to Alpha Centauri with what we have now, the answer is clear. Longer than we've had civilization itself. That doesn't mean we shouldn't try, but we have to understand the current limitations. Beamed propulsion and the problem of aiming a laser across light years. Beamed propulsion is one of the most talked about ideas in the effort to reach the stars. The laser-based approach to beamed propulsion is almost the opposite of how rockets work. With rockets, you carry everything with you, which makes you heavy and slow. But if you can beam energy to the spacecraft from the ground or from an orbiting platform, you leave all that heavy equipment behind. The spacecraft becomes little more than a sail and a payload, maybe no bigger than a smartphone. The plan for the Breakthrough Starshot team is to use a giant phased array laser system, maybe dozens of square kilometers in size, to fire incredibly powerful beams at a tiny spacecraft riding a light sail. But what looks clean and simple on paper hides huge technical problems. The biggest of them all is aiming. Light doesn't stay in a narrow line forever. It spreads. Even lasers, which are much tighter than ordinary light beams, still diverge over long distances. This is a basic result of physics. It's called diffraction, and it comes from the wave nature of light. Even a perfect laser beam starts to widen the farther it travels. The amount it spreads depends on two main things: the wavelength of the light and the size of the mirror or lens used to focus it. If you try to focus a beam of light using a mirror or lens 10 kilometers wide, that might sound huge, and it is. But even that kind of structure can only keep a laser beam tightly focused for a few million kilometers before it starts to spread out. By the time the beam reaches a target several light years away, it's no longer a narrow stream of energy. It's a wide, diffuse spot, often thousands or even millions of kilometers across. That means most of the energy is no longer hitting the sail. To keep the beam focused over such a distance, you'd need optics of impossible size. In some estimates, a mirror hundreds or thousands of kilometers wide would be needed to keep a tight beam on a sail traveling to Alpha Centauri. That's not something we can build today. It might not even be something we could build with any material we know of. The mirror or lens would have to hold its shape with atomic precision across an enormous span, while either floating in space or orbiting Earth. And it would need to point with extreme accuracy. A small error in aiming at the beginning can become a huge miss over light-year distances. Even if you could focus the beam perfectly for the first few thousand kilometers, just a small nudge or vibration can cause the beam to drift. There's no easy way to fix this mid-flight. Light takes over 4 years to reach Alpha Centauri, so any feedback system that waits for a return signal to correct the aim is too slow to be useful. You have to get it right the first time. That's why some designs propose using swarms of satellites to track the sail and correct the beam in stages. But that adds cost and complexity. Now, you need not just one giant laser, but hundreds or thousands of smaller systems in space, working together perfectly for years. You also have to keep the sail stable. If it tilts or wobbles even a little, it could veer off course or tear apart under the stress of the beam. That's especially true during the acceleration phase, where forces might reach thousands of Gs for a small craft. The amount of power needed to accelerate even a gram-scale spacecraft to a significant fraction of light speed is enormous. We're talking gigawatts to terawatts, more than the total output of many nations. Even if you pulse the beam only for a few minutes, the infrastructure needed to generate and control that kind of energy is staggering. And again, most of that energy is going to be lost due to beam spreading. You can work around this by increasing the sail size, but that brings problems of its own. A larger sail is heavier and harder to stabilize. The sail material must be almost perfectly reflective and extremely thin. It must resist heat, micrometeorites, and the pressure of high-powered light. Graphene and other advanced materials are often proposed, but none have yet been built at the scale or quality needed. One potential compromise is to aim for smaller missions. Instead of sending a large probe, you send tiny gram-sized payloads that carry cameras, communication systems, and power supplies in miniature. These chipsats ride on sails only a few meters across, and the entire package weighs less than a chocolate bar. With enough laser power, they can still reach very high speeds. But at this scale, communication becomes difficult. A tiny transmitter can't easily send a signal back to Earth from light years away, and the instruments it can carry are very limited. Still, for the near future, this may be our best bet. Beamed propulsion makes sense if your goal is to get something, anything, to another star quickly. It avoids the mass penalty of carrying fuel. It avoids many of the dangers of human spaceflight. It simplifies launch by keeping most of the hardware on Earth. But the price you pay is precision. Precision in aiming, precision in construction, precision in timing. The beam must fire at exactly the right angle, with exactly the right strength, for exactly the right duration. None of this is impossible, but none of it is easy. We've never built a laser powerful enough or an optic large enough to carry out this kind of mission. We've never guided anything with that level of accuracy over billions of kilometers. These are the kinds of challenges that live on the edge of engineering and physics. Solving them may take decades or perhaps even longer, and even if we solve them, we still won't be sending people. Solar sails and the curse of diminishing sunlight. The key to making a solar sail work is building it as light as possible. The sail itself needs to be incredibly thin, just microns thick, often thinner than a human hair, and highly reflective. Materials like aluminized mylar or captain have been used in test missions. These sails are unfolded in space and stretched out across wide frames. The larger the surface area, the more sunlight it can catch, and the stronger the force it can use to accelerate. Once deployed, the sail starts to pick up speed slowly. In space, where there's no air resistance and no friction, the acceleration continues to build. A solar sail can keep picking up speed for months or even years. But the farther you get from the sun, the weaker the push becomes. The amount of solar energy hitting a square meter of sail drops with the square of the distance from the sun. At Earth's distance, a square meter of sail might feel a pressure of about 9 micronewtons, but by the time you get to Jupiter, that same sail feels just 1/25th of that. Out near Pluto, the push is almost gone. This limits what solar sails can do. They work best in the inner solar system, where sunlight is strong. That's why many proposed missions using solar sails focus on orbits close to the Sun. Some even suggest sending a sail inward first, diving toward the Sun before swinging back out. Near the Sun, the light is much more intense. That means stronger acceleration. A sail that swings in close can pick up speed fast, then use that momentum to head out toward the planets or even the stars. But it's not easy to get close to the Sun. The heat can damage the sail, warp the structure, or even tear it apart. Materials that work well in cooler parts of space may not survive near the Sun's blazing energy. Engineers have to balance the benefits of high acceleration with the risks of thermal destruction. Because of these limits, some have proposed hybrid systems. One idea is to start with sunlight as the power source, but then switch to artificial light once the spacecraft gets too far from the Sun. This is where lasers come back into the picture. A laser array could take over, beaming high-powered light at the sail once the Sun's rays become too weak. In this jettison-to-laser hybrid approach, the spacecraft begins its journey like a traditional solar sail, relying on natural light to build speed. Then, maybe past Mars or beyond Jupiter, a laser picks up the job. By using solar power early on, it avoids the need for massive amounts of artificial energy right at launch. The laser array can be activated only when needed, and its focus can be tailored to where the sail is at any moment. But switching from sunlight to laser light isn't as easy as flipping a switch. The sail must be designed to reflect both kinds of light. It also has to be aligned with incredible precision to catch the beam. And the laser itself, as explained before, must remain tightly focused over long distances. Another issue is that solar sails, by design, have very low mass. That's good for acceleration, but bad for stability. These sails can be easily disturbed by micrometeoroids, by slight variations in light pressure, or by forces from the spacecraft's own control systems. Some designs use spin to stabilize the sail, much like a spinning top stays upright. Others rely on shifting the center of mass or adjusting small control vanes to steer. These systems add complexity and increase the risk of mechanical failure. And once a sail goes off course, it's hard to recover. There are no brakes and you can't easily turn around. Some advanced designs imagine sails kilometers across. Others picture networks of sails flying in formation, working together to reach higher speeds or carry heavier payloads. But building such structures would take time, money, and new materials. Right now, we're still learning how to build even small solar sails that work reliably. Even if we solve all those problems, the issue of weak sunlight in the outer solar system won't go away. A sail that works beautifully near Earth may become nearly useless once it passes Saturn. For deep space missions, especially interstellar ones, sunlight simply doesn't provide enough force. That's why more attention is being paid to the laser-backed versions. With enough investment, a laser array could beam energy to a sail far beyond the Sun's reach. But that pushes the problem back to Earth. It also raises political and environmental concerns. A laser strong enough to push a spacecraft at high speed could, in theory, damage satellites or even reach Earth's surface if misaligned. That makes governments nervous. So, while solar sails offer a quiet, steady way to move through space, they come with limits. They are elegant, but they are slow, and their usefulness fades with distance. Unless we find a way to extend their range, through lasers or something more exotic, they may never be more than local travelers. Fusion drives. Still a decade away since 1950. Fusion has long been the dream. If we could build a working fusion rocket, we'd have the best of both worlds, high thrust and high efficiency. A fusion-powered spacecraft could cross the solar system in months. Some designs even hint at travel to nearby stars in decades. But for over 70 years, the promise has stayed just out of reach. In the 1950s, scientists knew that if you could control fusion reactions in space, you'd have a nearly perfect propulsion system. The fuel is light, compact, and energy-dense. The exhaust from a fusion reaction moves incredibly fast. That means a fusion rocket could accelerate longer and reach higher speeds, all without the heavy fuel burden. There are two main ways people have proposed to trigger fusion in a spacecraft: magnetic confinement and inertial confinement. Both come from decades of work done in fusion energy research here on Earth. The magnetic version is built around a concept known as a tokamak, a donut-shaped chamber where magnetic fields trap hot plasma long enough for fusion to occur. The other, inertial confinement, uses tiny fuel pellets and blasts them with powerful lasers or particle beams to compress and heat them until they ignite for a brief moment. On Earth, both methods have seen progress. Huge projects like ITER in France are trying to prove that magnetic confinement can produce more energy than it consumes. In the US, the National Ignition Facility has managed brief flashes of fusion using high-energy lasers. But even after decades of research and billions of dollars, no reactor has yet produced steady, usable power. Controlling a fusion reaction is like trying to keep a tiny star suspended inside a box made of magnets or light. The temperatures needed for fusion are over 100 million degrees, hotter than the core of the Sun. Nothing solid can touch that. Everything must be contained indirectly, either by force fields or momentary pulses. Now imagine taking that fragile, complicated setup and putting it inside a spacecraft. That's where the challenge becomes even more extreme. A fusion reactor, even on Earth, needs massive systems to run. You need strong magnetic fields, cryogenic systems, and complex electronics. In space, you don't have access to large power plants or backup generators. Everything has to be self-contained and lightweight. And yet, to ignite fusion and keep it going, you need massive amounts of energy up front. Second, there's the issue of heat. Fusion reactions release a lot of energy in the form of heat and radiation. On Earth, reactors can use cooling towers, thick radiation shielding, and heat exchangers. In space, heat doesn't just flow away. You have to radiate it, slowly, through large surface areas. That means more mass, more complexity, and more things that can go wrong. Third, plasma containment in a moving, vibrating spacecraft is far more unstable than in a grounded, controlled facility. Magnetic fields can be thrown off by motion, interference, or changes in temperature. Inertial fusion designs, which rely on precision lasers or particle beams, demand perfect alignment and timing. A tiny error, even less than a millimeter or a nanosecond, can cause the whole process to fail. Some early fusion rocket designs tried to work around this. The most famous was probably the Bussard ramjet, a concept from the 1960s. It imagined a spacecraft that would scoop up hydrogen from interstellar space using a giant electromagnetic funnel, then fuse it for thrust. But it turned out there isn't enough hydrogen in space for that to work, not in the way the design required. Another approach was the magnetic mirror engine, where plasma would be shot out the back of the ship using magnetic nozzles. That design had potential, but it too suffered from instability and energy inefficiency. On Earth, most fusion experiments used deuterium and tritium, which are easier to ignite but produce dangerous neutrons that damage materials and generate radioactive waste. In space, you don't want your ship becoming radioactive after just a few months of flight. So researchers have looked into alternative fuels like helium-3, which are cleaner but harder to fuse and even harder to find. Another area of research, called magneto-inertial fusion, tries to mix both magnetic and inertial methods. Instead of huge tokamaks or giant lasers, these systems would compress plasma using fast-moving magnetic fields or metal liners. Some of these ideas are being explored for Earth-based power, but the designs are still early and unproven. So why does fusion always seem to be 10 years away? It's partly because each new breakthrough brings new challenges. Just getting ignition, where the reaction releases more energy than it takes to start, isn't enough. You need to sustain that reaction, control it, convert the energy into usable thrust, and manage the heat, radiation, and fuel supply. Every one of those steps requires its own technology, and they all have to work together perfectly. On a spacecraft, failure is fatal. A tiny leak, a short circuit, or a misalignment could shut down the engine, or worse, cause an uncontrolled reaction. Fusion may be clean in theory, But in practice, it's a roaring, unstable fire that wants to escape. Despite the risks, fusion propulsion remains one of the most appealing paths forward. Chemical rockets are nearing their limits. Ion drives are slow. Nuclear thermal engines promise a step up, but fusion, if it ever works, would be a leap. Private companies, military agencies, and international teams are all continuing to experiment. Some startup groups have claimed to be on the verge of compact fusion engines that could fit on trucks or spacecraft. Others are more cautious, aiming for proof of concept before talking about propulsion. Meanwhile, scientists continue to chip away at the physics. Better magnetic confinement, smarter fuel handling, new materials that can survive neutron bombardment. No one knows exactly when fusion will finally become practical. The timeline keeps shifting, but the interest hasn't faded because the reward is so large. A functioning fusion drive would redefine space travel. It could mean fast trips to Mars, months to the outer planets, and reaching another star within a human lifetime. Antimatter engines and the scarcity of annihilation fuel. Of all the propulsion ideas ever imagined, none comes close to the raw, staggering power of antimatter. It's the holy grail of rocket fuel, one where the very act of contact between particles and their mirror opposites unleashes energy with perfect efficiency. When matter meets antimatter, both vanish in a flash of pure energy. There's no leftover ash, no spent fuel, just an enormous outpouring of radiation. It's the cleanest and most powerful reaction allowed by physics. In terms of energy per gram, antimatter outclasses everything. Even nuclear fusion looks tame by comparison. The numbers are hard to believe. 1 gram of antimatter reacting with 1 gram of ordinary matter releases about 90 terajoules of energy. That's roughly equal to the explosive power of 21 kilotons of TNT, the same size as the bomb dropped on Nagasaki, and that's just from 2 grams. In theory, if you could carry just a few kilograms of antimatter and convert it safely, you could drive a spacecraft across the solar system in days, or reach the nearest stars in a fraction of a human lifetime. The exhaust velocity would be enormous. There would be no need for oxidizers, no heavy fuel tanks, no reliance on sunlight or gravity assists. It would be the closest thing to a magic bullet. But the reality is far from that dream. Antimatter exists. We've seen it in nature and created it in labs. But it's so scarce and so hard to make that the idea of filling a spacecraft with it is still entirely theoretical. Antimatter is the mirror image of normal matter. The antiparticle of the electron is the positron, with the same mass but a positive charge. The antiparticle of the proton is the antiproton, with a negative charge. Put the two together, an antiproton and a positron, and you get an antihydrogen atom. Scientists have produced antihydrogen in experiments. They've even trapped it for a few minutes inside complex magnetic cages to study its properties. But we're talking about individual atoms. In some cases, a few thousand or a few million at most. To fuel a working rocket, you'd need grams of antimatter. That might sound pretty doable, but current particle accelerators produce antiprotons in such tiny quantities that the annual global output is measured in nanograms, billionths of a gram. At those rates, producing a single gram would take millions of years, and it would cost more than the entire GDP of Earth. The most optimistic estimates place the cost of antimatter at trillions of dollars per gram. Creating antimatter means slamming protons into targets at near-light speeds inside giant particle accelerators. The resulting collisions create showers of particles, including a tiny number of antiprotons. These antiprotons must be collected, slowed down, cooled, and stored. Each step loses particles. The overall efficiency is dismal. For every million protons you smash, you might get 1 usable antiproton. And the equipment to do this is massive, power-hungry, and incredibly delicate. Even if we could improve the efficiency and reduce the cost, there's still the question of storage. Antimatter cannot touch matter. The moment it does, it annihilates. That includes the walls of any container, the air around it, even a speck of dust. So you can't just pour it into a tank or freeze it into a pellet. You have to suspend it using electromagnetic fields inside a perfect vacuum, isolated from all physical contact. It has been done on a microscopic scale. The penning trap is one such device. It uses a combination of electric and magnetic fields to suspend charged particles in space. Physicists at CERN have used it to trap antiprotons for minutes and even combine them with positrons to form antihydrogen atoms. But storing grams of antimatter this way would require magnetic bottles many times more stable and reliable than anything we've ever built. And they would have to work perfectly, without failure, for years at a time. Any glitch, any power loss, or physical breach would result in an instant, catastrophic explosion. Antimatter particles must be slowed and kept cold to remain trapped. That means operating at cryogenic temperatures, adding more complexity and more failure points. In space, where extreme temperatures already challenge engineering limits, adding a cryogenic, high-voltage, magnetic containment system for a substance that will vaporize your ship if mishandled, even slightly, is an enormous burden. Some spacecraft designs try to work around this by not storing large amounts of antimatter. Instead, they use it in tiny doses to ignite fusion reactions or to heat conventional propellants. In one proposal, called an antimatter-catalyzed microfission/fusion engine, antiprotons are injected into small pellets of nuclear material. The annihilation triggers a miniature explosion, which then drives a standard rocket nozzle. This reduces the amount of antimatter needed, but still requires stable storage and precision delivery of antiprotons, things we don't know how to do at scale. Other concepts are even more speculative. Some suggest we could collect natural antimatter trapped in Earth's magnetic field, or possibly from the belts around gas giants like Jupiter. There is some evidence that antimatter exists in trace amounts in these regions, but the densities are so low that you'd need giant collection surfaces and long time frames just to gather micrograms. There's also the idea of antimatter factories in space, vast solar-powered accelerators orbiting the Moon or floating near the Sun, using collected energy to synthesize antimatter continuously. These are technically possible, but would require a level of infrastructure and investment far beyond anything we've built so far. It would be like building a Saturn V every week, for decades, with no immediate return. Then there's the military concern. Even a few milligrams can create explosions larger than conventional bombs. Grams would rival small nuclear weapons. Any nation that could produce, store, and control antimatter would have unprecedented destructive power. That makes it a political and security risk, as well as a scientific challenge. Despite all this, antimatter research continues, slowly. Experiments at CERN and other labs are teaching us more about how antimatter behaves. Better traps are being designed, new accelerators are being planned. And in the far future, if costs can be reduced and containment made reliable, antimatter may play a role, not in full-scale engines perhaps, but in triggering high-efficiency reactions or in compact high-thrust stages for deep space missions. But for now, the gap between what's possible in a lab and what's needed for a working propulsion system remains vast. The energy is there, waiting, but everything else is still unanswered. The Alcubierre drive, bending space or breaking physics. First proposed in 1994 by theoretical physicist Miguel Alcubierre, the Alcubierre drive offers a strange loophole in Einstein's general theory of relativity. Instead of moving a spacecraft through space in the usual way, accelerating it with rockets, burning fuel, or riding photons, this concept suggests bending space itself. The ship doesn't move forward, not in the way we normally think of motion. Instead, it stays still inside a kind of bubble, while the space in front of it contracts and the space behind it expands. The ship rides this distortion like a surfer on a wave, moving through the universe without ever locally exceeding the speed of light. At first glance, it seems impossible. Einstein's equations famously forbid faster-than-light travel for any object with mass. As a rocket accelerates toward light speed, its mass increases, and the energy needed to keep pushing it rises dramatically. At light speed, that energy becomes infinite. No matter how advanced your engine, you hit a wall. But general relativity doesn't ban space itself from expanding or contracting at any speed. The early universe did just that during inflation, expanding faster than light in all directions. The Alcubierre drive exploits this quirk. It doesn't push a ship faster than light through space. It moves space itself around the ship. The mathematics behind this are not simple, but the basic idea comes down to what's called a warp bubble. This is a region of flat space-time, normal space in which the ship sits, surrounded by a shell where the geometry is twisted. In front of the bubble, space is compressed. Behind it, space is stretched. As this whole region slides forward, the ship goes along for the ride, even though, from its own point of view, it never really moves. This isn't reactionless propulsion, like the discredited EM drive or similar fringe ideas. Those claim to push a craft without ejecting mass or interacting with anything external, violating momentum conservation. The Alcubierre drive doesn't break momentum laws. It's not that kind of motion. The drive system doesn't push the ship forward. It changes the shape of the space the ship sits in. That's a key difference. It's still consistent with general relativity, at least on paper. But while the mathematics works, in a theoretical way, the energy requirements are beyond anything remotely practical. To create the space-time curvature needed for the warp bubble, the equations demand what's known as exotic matter, something that has negative energy density. This is something that, in effect, weighs less than nothing. It would repel gravity instead of attracting it. Normal mass curves space inward. Exotic matter, if it exists, would curve it the other way. We know from quantum theory that certain strange effects, like the Casimir effect, do seem to involve negative energy, at least in a narrow and fleeting sense. Two metal plates placed close together in a vacuum can experience an attractive force due to suppressed vacuum fluctuations between them. This suggests that the energy in that region is, in a way, negative relative to the surroundings. But this is a tiny effect, measured in nanojoules. To bend space on the scale needed for a ship to ride a warp bubble, you'd need a vast amount of negative energy, many orders of magnitude greater. Early estimates of how much exotic matter would be required for a functional Alcubierre drive were staggering. Some calculations suggested you'd need more mass energy in exotic form than exists in the entire universe. Later refinements brought that number down to something closer to the mass of Jupiter, or even a few thousand kilograms. But even those lower figures assume a kind of exotic matter we have never produced or confirmed in any form, let alone in useful quantities. And they rely on idealized geometries, thin shell models, and other simplifications that may not hold up in real-world physics. A warp bubble once formed might be unstable. Some simulations suggest that the bubble could collapse or emit destructive radiation when turned on or off. There's also concern about how a ship inside the bubble could interact with the outside world. Since the bubble moves faster than light relative to the space around it, no signal could pass through the front edge. The ship would be causally disconnected from the universe ahead of it. That means the crew couldn't steer, brake, or communicate, at least not until the bubble ends its journey and the geometry reverts to normal. Another issue is that the formation of the bubble may create extreme tidal forces. Just as falling into a black hole would stretch you out along one direction and compress you along another, a badly formed warp bubble might tear apart anything inside. Some solutions have been found to smooth out these tidal effects, but they depend heavily on the precise arrangement of the exotic matter, again assuming it can be engineered at all. There are more practical concerns as well. If the warp bubble scoops up particles from the interstellar medium as it travels, they might build up along the front edge, like debris on a bow wave. When the bubble collapses, all of that energy and matter would be released in a concentrated burst, potentially frying everything in the destination zone. This kind of wake effect might make the drive unsafe, even if it could be built. The Alcubierre drive remains an intriguing theoretical construct, but at present, it's not a technology. It's not even close. It's a solution to the equations of general relativity under highly unrealistic conditions. It shows that the laws of physics don't strictly prohibit faster-than-light travel if space itself is manipulated. But getting from that insight to a working machine would require breakthroughs in quantum field theory, materials, science, energy generation, and containment technology that we can't even define yet. Some researchers are trying to modify the original idea to make it more plausible. There have been proposals for naturocubic warp geometries that reduce the need for exotic matter by reshaping the bubble. Others suggest designs where the drive moves at subluminal speeds but still benefits from space-time manipulation to reduce travel time. These approaches try to stay within more reasonable energy budgets and may provide testable predictions in the future, but they're still highly speculative. The Alcubierre drive is a glimpse into what might be possible, not a blueprint for a warp ship. And for now, that's where it stays. The psychology of 10,000-year missions. When we imagine an interstellar voyage using conventional propulsion technologies, there are generally two kinds of mission concepts. One is the small, long-duration crew, maybe a few dozen people, carefully selected and supported by advanced AI and automation. The other is the generation ship model, a large, self-contained world with hundreds or even thousands of people, living and dying aboard the vessel for centuries or millennia, with only their distant descendants reaching the destination. Both approaches come with very different psychological demands. In a small crew scenario, isolation is extreme. Even in modern space missions aboard the International Space Station, where missions last just 6 months, astronauts face real mental strain. They're cut off from the natural rhythms of Earth. The social environment is limited, and even small irritations can escalate over time. In a voyage that could last 10,000 years or beyond, that isolation becomes something far more complex. For a small crew, even the idea of returning home vanishes. Earth, as they know it, is already gone long before the halfway mark. They are flying into a future in which no part of their birth world still exists in any familiar form. Without outside contact, a crew like this would become a closed loop, socially, emotionally, and culturally. Messages from Earth would become increasingly delayed and eventually meaningless. A single radio transmission from Earth would take over 4 years to reach even the closest star systems. After just a few centuries, the crew would be receiving messages from a planet and a society they could no longer understand or relate to. And eventually, the messages would stop altogether. What does it mean for a human mind evolved to live in a social group on a rotating planet under the sky, to be locked in a metal can, drifting through the black, with only the hum of machinery and the same few voices for company? Researchers studying confinement environments have looked at analogues like Antarctic stations, submarines, and polar outposts. These situations show that long-term isolation often leads to symptoms like depression, disrupted sleep cycles, increased irritability, and emotional blunting. Even with recreational systems and good communication, people begin to withdraw. Time can lose its structure, events feel repetitive, mental health becomes fragile. For a space crew on a centuries-long mission, these effects could become amplified in ways we've never experienced before. Automation might ease the burden, but it also reduces stimulation. A ship that mostly flies itself might seem safer, but for the humans aboard, boredom becomes a kind of slow-burning danger. With few challenges and fewer surprises, the brain can spiral inward. Long-term confinement can feed into what psychologists call sensory monotony, where the lack of new inputs begins to affect cognition, mood, and even memory. Then there's the other kind of mission, the generation ship. Instead of a small crew enduring an impossibly long flight, a large number of people are sent on a one-way trip in which they and their descendants will live, reproduce, and die aboard the ship for hundreds of generations. This model, often imagined as a massive rotating habitat with a closed ecosystem, avoids the need for suspended animation or centuries of boredom by simply accepting that the original crew will never see the destination. In some ways, the generation ship concept is more realistic, culturally at least. People aboard such a ship wouldn't be waiting, they'd be living, the ship would become their world. They'd have schools, families, traditions, and eventually entire social systems that develop independently. But this brings its own set of challenges. What happens to identity on a ship like that? The first generation knows they came from Earth. Maybe the second and third are raised with that knowledge. But after a few hundred years, it becomes abstract, a myth, a place in history books or digital records. The people born on board wouldn't feel like passengers. They would feel like citizens of a sealed world. The destination, Alpha Centauri or Proxima b, would be just another myth. If things go well, their descendants will arrive. But for those living in the middle of the timeline, the ship is all they've ever known. This long middle period presents unique risks. Motivation might fade. Cultural drift could lead to apathy or resistance toward the mission itself. Over generations, belief systems might change. Perhaps some factions want to turn the ship around or abandon the mission altogether and remain in deep space, seeing the mission as irrelevant. Some societies might lose sight of the mission's goals entirely, treating Earth's instructions as ancient fables. Keeping a crew emotionally and socially aligned across millennia might require forms of cultural engineering we've never attempted. One approach might be to institutionalize the mission, turn it into a kind of religion or unifying ideology. Rituals, symbols, and origin myths could keep the destination meaningful across centuries. But this has risks of its own. Belief systems can evolve in unpredictable ways. They can become rigid, exclusive, or oppressive. They can also fragment. Schisms and political struggles aboard a sealed ecosystem could destabilize life on board and lead to resource disputes, breakdowns in authority, or even violence. Another major challenge is population stability. On a ship meant to operate for thousands of years, even small deviations in birth rate, death rate, or healthcare outcomes can, over time, result in large swings. Overpopulation strains resources. Underpopulation leads to genetic bottlenecks or labor shortages. Psychological well-being is directly tied to these pressures. A society living in scarcity tends to become anxious, risk-averse, and sometimes aggressive. A society that is too comfortable might become complacent or lose its sense of purpose. A ship with a fixed population and limited gene pool must manage reproduction carefully. Who can have children and when? Who decides? What happens when personal desires conflict with communal needs? These questions, if not resolved, can tear a society apart. Human relationships are complicated even on Earth, where we have space, privacy, and escape. On a generation ship, privacy is minimal and the social environment is tightly constrained. Jealousy, exclusion, and power dynamics could take new forms under such pressure. Every generation must learn not just how the ship works, but why it exists. Technical skills, yes, but also history, values, and the fragile truth that they are part of a bridge, not an endpoint. And this education must be adaptable. Over centuries, the technology of the ship may change through repair, jury-rigging, or innovation. Cultural values may evolve. Language itself might drift. The ability to keep the crew socially coherent, while also allowing for growth and change, is a balance few societies have ever managed for long. There is also the matter of grief. Not just personal grief, but cultural grief. The people on a 10,000-year mission are saying goodbye to Earth in a deep, permanent way. For the first few generations, there may be a longing for the home they left behind. For later generations, there may be a sense of loss over their origin, or confusion about what that origin even meant. For the final generations, arriving at the destination may feel like reaching a place they were never meant to go. Maintaining psychological resilience across this arc is an enormous challenge. Humans need stories, goals, and identities to keep going. A 10,000-year mission stretches all of those to their limits. Whether the crew is 20 people or 20,000, the psychological risks are profound. More than any other part of the mission, they may be the hardest to design around. Can humans survive in a sealed metal tube for generations? A starship built for generations is an ecosystem, a tiny closed version of Earth, sealed off from any outside help. Closed-loop life support is the technical term for what that kind of ship would need. Everything people eat, drink, and breathe has to be reused. There is no supply ship arriving with fresh vegetables, no outside waste disposal, no backup water tank. On Earth, nature does all this work invisibly. Plants recycle carbon dioxide into oxygen. Microbes break down waste into nutrients. Rain filters water. On a ship, all of these systems must be built, monitored, and kept running forever. Early space missions already had to carry limited resources and recycle some of them. The International Space Station, for example, recycles water from urine, sweat, and the air. Oxygen is partly generated by breaking down water molecules. But even the ISS is not a true closed loop. Supplies still arrive from Earth regularly, and the missions are temporary. A generation ship must function without any of that. The first major attempt to explore this on Earth was Biosphere 2. In the early 1990s, 8 people sealed themselves inside a huge glass structure in the Arizona desert. It had a mini ocean, a rainforest, a savanna, and a farm. The goal was to live off the land inside, recycling water, air, and nutrients without help from the outside world. It was supposed to be a small, self-sustaining world. It didn't go smoothly. Within a few months, oxygen levels started to drop. Carbon dioxide was absorbed by the concrete, making it unavailable to plants. Food became scarce. The crew lost weight and energy. Psychological tension grew. Arguments became common. Insects like ants and cockroaches thrived while other species died out. Even though the mission lasted 2 years, it exposed just how delicate a closed system can be, even when carefully planned. On a real starship, there is no room for experiments like that. Oxygen must be constantly replenished. Carbon dioxide must be scrubbed. Food must be grown, harvested, and reused in a steady cycle. Every human on board produces waste, and that waste has to be turned back into nutrients. There's no landfill, no sewer system leading anywhere else. Every drop of water must be caught and cleaned. Every calorie must be accounted for. That means building a life support system that's not only closed, but also stable and balanced for centuries. Even a small imbalance can have huge effects over time. Too much nitrogen, and plant growth slows. Too little oxygen, and people get sick. Too much humidity, and molds or bacteria can take over. If a single crop fails, the food system might collapse. If one microbial population grows out of control, it could ruin the water supply. And on top of that, everything breaks eventually. Pumps wear out, filters clog, pipes leak, electronic systems degrade. Keeping these systems running requires having the right knowledge and skills passed from one generation to the next. A ship like this needs a culture that values maintenance, understands biology, and teaches every child how their world works. Because if even one generation forgets, the whole system could fail. You can't store 1,000 years of food, it has to be grown. That means hydroponic or aeroponic systems, plants grown in water or mist with artificial light. It also means recycling human waste into fertilizer. This is biologically sound, but culturally complex. On Earth, many societies have taboos around waste. On a starship, those must be rethought. What was once trash becomes a resource. Protein is especially hard to manage. Traditional livestock require too much space and food. Insects are a likely solution. They're high in protein, grow quickly, and can be raised on scraps. Algae is another possibility. It grows in water, absorbs carbon dioxide, and can be turned into food or oxygen. Fungi may also play a role, breaking down waste and turning it into edible biomass. But none of these look or taste like what people are used to. A starship crew has to be culturally ready to accept this new diet and pass that acceptance onto the next generation. Population management is equally important. In a sealed ship, if too many people are born too quickly, the system crashes. But if too few are born, the population shrinks, and there may not be enough people to keep the ship running. This requires careful control of fertility, not just through technology, but also through culture. Some proposals suggest mandatory birth licenses or reproductive quotas. Others suggest voluntary systems, based on education and incentives. A society raised on Earth might resist these kinds of controls. But a society raised in a starship might see them as normal, as essential. In a closed society, ideas bounce around, get amplified, and turn inward. A small myth can become a major belief. A minor rule can become a strict taboo. Without outside correction, cultures can drift into strange shapes. This isn't necessarily bad, but it means unpredictability. The idea of reaching a planet may turn into legend or be dismissed as a lie. Education is the main tool to fight this drift. Every generation must understand where they came from, why the ship exists, and what its purpose is. That means creating libraries, preserving language, and building institutions that can adapt without collapsing. Even entertainment matters. Stories, games, and art help carry culture forward. They give people meaning, joy, and connection. A sterile ship with perfect engineering but no shared culture is a recipe for psychological breakdown. Crisis management must be part of the design. Accidents will happen. Systems will fail. People will get sick. The ship needs not just doctors and engineers, but also mediators, counselors, and leaders. There must be systems for justice, conflict resolution, and social healing. The smallest dispute left unresolved can grow into resentment. And resentment in a closed system is a dangerous thing. This is why some researchers suggest that building a self-sustaining society in space is less about hardware and more about social design. The hardware must work, of course, but the people must also believe in the mission, understand their world, and trust each other. They must be able to adapt without panic, change without collapse, and stay united without outside help. How many humans are needed to seed a star system? Humans inherit half of their genetic material from each parent. Too small a population, and you start to see serious genetic problems. Inbreeding, where close relatives have children, increases the chance of recessive genetic disorders showing up in offspring. On Earth, isolated populations over history have sometimes struggled with this. The most well-known are royal families that intermarried for generations, but even remote communities today show higher rates of some genetic diseases. These real-world examples have helped scientists model how many individuals are needed to keep a population healthy over time. Population genetics studies often work with two numbers. One is the census population, how many people are physically present. The other is the effective population, how much real genetic variation is being passed on. In a tightly closed system with limited mating options, the effective population tends to shrink over generations, even if the census population stays the same. That's because relatives tend to be more genetically similar, so the pool of diversity isn't refreshed. Models suggest that to maintain a healthy gene pool over centuries, you need at least several hundred people. Some studies put the minimum at around 160 to 200 people for very strict conditions, assuming perfect planning and mate selection. But this assumes very careful reproductive control, strong medical technology, and lots of cultural stability. Other models, especially those that assume less than ideal conditions, suggest that a crew of 500 to 1,000 would be much safer. This allows for enough genetic variation to survive random events, losses, or social disruptions. Still, even 1,000 people might not be enough if the goal isn't just to survive on a ship, but to settle a new world. When the settlers step off the ship, they'll need to be healthy, fertile, and culturally unified enough to face the challenges of a new planet. They'll need doctors, engineers, farmers, teachers, and builders. They'll need to make tools, grow food, raise children, and deal with unexpected problems. That means redundancy. You can't send one doctor and hope nothing happens to them. You need backups, people who can fill roles if someone dies or becomes unable to work. That pushes the needed number even higher. Some estimates say 5,000 people would be the minimum for a truly self-sustaining colony with natural growth, strong health, and long-term survival. These numbers come from simulations used in everything from conservation biology to space mission planning. The principles are similar to managing endangered species. The more genetic diversity, the more resilient the population is over time. But there's a tension here. Modern technology is pushing in the opposite direction, toward miniaturization, automation, and minimal crew sizes. Projects like Breakthrough Starshot imagine tiny probes flying to Alpha Centauri with no humans on board. In the context of larger ships, some future missions imagine robotic caretakers watching over frozen embryos or artificial wombs. If people don't need to be awake during the trip, or if the first generation can be grown upon arrival, the size of the initial ship could shrink dramatically. This leads to ideas about an embryo space ark, a craft that carries not adult humans, but the genetic materials to create them. In this scenario, the ship could be small and lightweight, using automation and artificial intelligence to land, build infrastructure, and raise the first generation of humans using robotic systems. It removes the need to keep adults alive for the journey. But this idea depends on levels of technology and reliability that don't yet exist. Artificial wombs have not yet replaced real pregnancies. Parenting by robot is completely untested, and cultural transmission, teaching a child to speak, to trust, to work with others, can't yet be handled by machines. Research into artificial wombs is advancing slowly. Genetic storage and long-term embryo cryopreservation are improving. But even if these technologies become practical, they don't eliminate the need for genetic diversity. In fact, they make it even more important. A tiny colony grown from a few hundred embryos may lack the variation needed to resist disease, adapt to new environments, or avoid long-term defects. So even a minimal seed crew would still need to represent the genetic diversity of a much larger population, potentially requiring the careful selection of embryos from thousands of donors. Some scenarios try to blend the two approaches, send a small human crew along with a large genetic bank. The crew raises the first generation, acting as both parents and teachers. As the colony grows, more embryos are activated, increasing diversity without needing to send everyone on the ship. This approach still requires high survival rates, strong leadership, and a reliable medical system. If the first few generations fail, the entire mission fails. One often overlooked factor is social diversity. People need varied ideas, personalities, and skills. A society built entirely from one cultural background may have blind spots. A society with no artists or no historians would lose important knowledge. Diversity isn't just biological, it's also psychological, intellectual, and emotional. It helps societies adapt, solve problems, and avoid cultural stagnation. At the same time, diversity creates friction. Different values, different goals, and different personalities can lead to conflict. In a sealed ship or a small settlement on another world, those conflicts can turn deadly. That's why selection for starship crews must focus not only on genetics or intelligence, but on compatibility, cooperation, and emotional resilience. The people chosen must be able to live and work together, generation after generation. A crew of 500 might have enough genes to avoid inbreeding, but if they can't agree on rules, if they splinter into factions, or if they forget their mission, the numbers won't matter. The paradox of sending children to do our exploring. At the heart of exploration is choice. People who climb mountains or sail across oceans do so voluntarily. They weigh the risks, prepare for hardship, and go because they want to. That sense of choice defines what we consider heroic or pioneering. But on a generation ship, the people doing the real work would be born into it. They wouldn't have a say. They wouldn't get to choose to go or not go. They'd just be there in a ship they never signed up for, fulfilling a mission created by people long dead. Some defenders of the concept argue that this isn't very different from life on Earth. No one chooses to be born. Children in remote villages or urban slums also don't pick their surroundings. People everywhere are shaped by their environment and by what came before them. The difference with a generation ship, though, is that the limitations are absolute. You can't walk away. You can't travel or emigrate or make a new life in another part of the world. Your whole universe is the ship. Every choice has already been shaped by engineers, planners, and psychologists you've never met. That creates a kind of social lock-in that has no counterpart on Earth. Others suggest that if the ship is designed well enough, if life on board is rich, stable, and full of opportunity, then the lack of choice won't matter. Children growing up inside such a ship would see it as normal. They might not even miss Earth, having never experienced it. If they're raised with a sense of purpose, they might even take pride in being part of a great mission. Much depends on the attitudes and behaviors of the founding crew. If the first generation creates a positive, inclusive culture with strong education and respect for the mission, the descendants might embrace their role. But if the early years are marked by hardship, division, or dysfunction, those patterns could repeat. Children raised in a tense, over-regulated, or pessimistic society may turn against the mission altogether. They might see it not as a noble cause, but as a prison sentence imposed by strangers. Some ethicists argue that no matter how good life on board might be, it's still wrong to lock future generations into a single path, especially if that path leads to a planet that might not even be habitable. What if the ship arrives and finds only rock, ice, or radiation? The descendants would have lived and died for nothing. In this view, the risk is not just physical, but moral. You are asking future people to carry the burden of your dreams with no way out. This stands in contrast to adult volunteer missions. In those, every crew member agrees to go, knowing the risks and the conditions. Their decision is informed. They can change their minds. Even one-way missions to Mars have been discussed along these lines. Brave volunteers going to settle and die there, fully aware of the outcome. These missions don't raise the same ethical alarms because the choice is present. The person exploring knows what they're getting into. This leads to the idea that perhaps generation ships should not be launched at all. Instead, some suggest that we wait until propulsion is fast enough to allow living humans to make the journey themselves, either through suspended animation, faster engines, or some breakthrough in physics. Others return to the embryo ship model. No people at all, just genetic material, AI caregivers, and automation. That way, the first generation born at the destination would be the first to live, not just the next in line. But even this raises questions. If children are raised by machines with no living humans to guide them, is that better or worse than being raised in a ship? What kind of society would emerge from that? Would they feel human at all, or see themselves as something else? All these ideas circle back to the same issue. Can we ethically plan for people who can't speak for themselves? Who gets to decide the shape of future lives? Is it ever acceptable to lock generations into a journey they didn't choose in the name of progress? In fiction, generation ships often end in tragedy. Rebellions, forgotten missions, decayed systems. Sometimes the ship's purpose is lost entirely. These stories reflect our fears and the discomfort we feel when thinking about a future we can't control. For some, the idea of sending children to explore space is beautiful, a way to continue the species, to give life a new home. For others, it feels too much like control, too much like destiny forced on people who never asked for it. The dream of the stars, when stretched over centuries, becomes tangled in choices we can't take back. The line between exploration and imposition becomes hard to see. And so, even as the engineering progresses and the simulations improve, the question remains unanswered. Should we? Self-replicating probes and the grey goo of exploration. Self-replicating probes, sometimes called von Neumann probes after the mathematician who first laid out the principles of self-replicating automata, are imagined as the ultimate tool for spreading human presence, or at least human engineering, throughout the galaxy. They wouldn't need to return home, carry life, or be guided by radio. They would simply travel, land, build, and copy themselves, again and again, in a process limited only by time and available resources. The core idea is straightforward. A single probe is launched toward another star system. Once there, it searches for a suitable asteroid or small moon rich in metals and other useful raw materials. Using onboard tools like mining arms, refining equipment, and 3D printers, the probe begins to dismantle the rock, smelting and shaping parts for a second probe that's a copy of the original. Once the new probe is ready, it's launched to another system, where the process begins again. Each generation adds more probes, and with every replication, the total number grows. This kind of exponential expansion, where 1 becomes 2, 2 become 4, 4 become 8, is incredibly powerful. Even starting with a single probe, the number of copies can reach astronomical levels in a surprisingly short time. If each probe took only a few decades to travel, land, harvest, and build a new one, a web of these machines could span thousands of star systems in just a few million years. On cosmic timescales, that's practically instant. Building giant crewed ships to cross interstellar distances is expensive, risky, and slow. But a small self-replicating probe, perhaps no bigger than a car or even a briefcase, could do the job of surveying and mapping the galaxy at a fraction of the cost. If they're smart enough, these probes could collect data, look for habitable planets, test for signs of life, and send information back home. They could prepare sites for future human arrival, building infrastructure in advance, like automated pathfinders. In theory, these probes could also adapt to what they find. If they detect a world with intense radiation, they could adjust their design to shield the next generation. If they find metals in one form instead of another, they could change their smelting methods. If they're made to be flexible, modular, and software upgradable, they might improve over time, evolving like tools that learn as they go. But this idea also comes with serious risks, especially when the machines are designed to act on their own. If a probe malfunctions or its programming becomes corrupted, it might begin replicating without limits. Even worse, it might start harvesting any material it finds, not just designated asteroids. If a probe lands on a planet and starts dismantling the surface to make copies, the consequences could be catastrophic. In this scenario, the machines don't recognize boundaries or ecological harm. They just follow the goal to replicate. That's where the term grey goo comes from. Originally coined in relation to nanotechnology, it describes a nightmare scenario where self-replicating machines consume everything around them, turning the universe into a lifeless cloud of churning machinery. If even one flawed probe replicates in a dangerous way and spreads to other systems, it could set off a chain reaction. Once copies are made and launched, there may be no way to call them back. If they don't respond to signals or have no built-in kill switch, their spread might only be halted by natural barriers, such as running out of materials, hitting areas of deep space without stars, or colliding with unpredictable hazards. Otherwise, they could keep going. This leads to a deeper philosophical problem. If self-replicating probes are such an obvious and efficient tool, why don't we see them? The galaxy is over 13 billion years old. Even if only one advanced civilization had launched self-replicating probes a billion years ago, the machines would have had plenty of time to reach every star. But we don't see them. There's no clear evidence of alien probes in the solar system, no signs of artificial structures in nearby space. Some scientists see this as part of the Fermi paradox, the mystery of why the universe appears so silent, despite the math suggesting it should be teeming with intelligent life. One possibility is that civilizations avoid using self-replicating machines because the risks are too great. The fear of grey goo might be a very real concern for any species smart enough to build such technology. If one civilization tried it and lost control, the damage could have been so widespread that other civilizations either perished or made strict rules never to try the same thing. It's also possible that self-replicating probes need extremely careful oversight, with built-in restrictions and tamper-proof safeguards that stop them from growing unchecked. Another possibility is that we're not looking in the right way. A self-replicating probe doesn't have to be big, bright, or obvious. It might be the size of a toaster or smaller. It could land on an asteroid and sit there, blending in. If its goal is to observe or remain hidden, we might miss it entirely. In fact, there have been proposals that alien probes could already be in our solar system, hiding on distant moons or in the asteroid belt, waiting silently or monitoring from afar. Without knowing exactly what to look for, we might not even recognize them. If humans ever build self-replicating probes, the challenge will be balancing power with responsibility. On the one hand, these machines could map the galaxy, prepare new worlds, and act as ambassadors of Earth's technology. On the other, if even one of them breaks loose, the results could be irreversible. It's like creating a species of machines and letting them go, possibly forever. Designs for these probes would need strict fail-safes. One idea is to limit the number of generations. After, say, 5 rounds of copying, the machines shut down permanently. Another idea is to build in energy constraints. Probes that can only operate if they receive a coded beam from Earth, ensuring they're under constant supervision. More complex versions might use AI ethics modules, with programmed behavior that rejects replication unless conditions are exactly right. And then, there's the question of how far we want to spread in the first place. Sending out machines that copy themselves endlessly across the galaxy is a bold gesture. It says we want to touch everything, see everything, maybe even reshape everything. But should we? What if other life exists? What if some planets should be left alone? The technology might one day be possible, but the ethics may never be simple. A self-replicating probe is a seed. Once planted, it can grow in ways we may not fully predict or control. Whether it helps us reach the stars or becomes the start of something unintended will depend on how carefully we design, deploy, and, above all, respect the power we give it. The first artificial intelligence astronauts. Today, the robots we send into space are clever but limited. Mars rovers like Curiosity and Perseverance can drive over rough terrain, drill into rocks, and take pictures, but they don't make many choices on their own. Almost every movement is planned in advance by teams on Earth. Engineers send a list of commands during a window of communication, and the rover carries them out over the next Martian day. Even something as simple as turning around or adjusting its path is often reviewed carefully to avoid risk. The robots are slow and cautious by design. This approach works for nearby planets, where signals can go back and forth in minutes or hours. But it simply can't work for interstellar missions. If a probe is traveling to a star that's 10 light-years away, it would take 20 years to send a command and get a reply. In that kind of delay, no human team can guide a rover through rough terrain, fix a sensor failure, or respond to a sudden dust storm. The probe would have to figure it out alone. The next generation of robotic explorers may not just carry sensors and cameras, they may carry evolving digital minds. Minds that are trained to interpret their environment, recognize danger, plan repairs, and even form goals. These machines would decide what to do based on what they find. They'd be explorers in their own right, not just extensions of a team back home. To build that kind of intelligence, researchers are looking at a mix of machine learning, neural networks, and adaptive systems. A machine that sees a new kind of terrain should be able to study it, compare it to what it already knows, and adjust its walking or driving pattern to avoid getting stuck. If it encounters a material it can't drill into, it should test other tools until one works. If a storm blocks its solar panels, it should find shelter and conserve power without being told. This kind of flexibility is much harder than it sounds. Current AI systems are very good at one task at a time. Teaching an AI to be adaptable means teaching it not just how to act, but how to learn. It means giving it curiosity, caution, and creativity, qualities that are hard to define in software. One way researchers might build this is through simulation. Before sending a probe into space, they could let it live in a virtual environment where it would face thousands of challenges: falling rocks, equipment failures, toxic gases, unstable ground. The AI is rewarded for surviving and learning. Over time, its responses become more refined. When it's finally ready to launch, it carries a library of experiences shaped by millions of simulated days. And once it's out there, the learning doesn't stop. The AI keeps updating its memory, improving with each encounter. This method is already being tested on Earth in experimental robots that walk through forests, climb over rubble, or explore ocean floors. Some can identify patterns in heat, sound, and movement. Others can communicate with each other, sharing data to improve group behavior. These are still early steps, but they show what might be possible. In space, the demands will be even greater. A self-learning probe might have to repair its own systems using spare parts, reroute circuits after damage, or print a new limb from onboard materials. It might need to study a planet's chemistry to avoid landing in acidic regions. It might even have to understand the difference between a strange natural formation and something artificial, something made by another intelligence. If such a robot finds evidence of life, how should it react? Should it approach? Should it avoid contact? Should it send a message? An intelligent probe would need ethical programming too, guidelines for when to act and when to hold back. This adds another layer of complexity. The way these probes are designed could also affect their personalities. If the goal is to make a quiet, careful scout, the AI might be cautious and reserved. If the goal is to explore aggressively and take risks, the AI might be bold and curious. The emotional tone of these machines, even if they don't feel emotion like we do, could shape how they behave over time. A probe that feels fear in dangerous conditions might survive longer. One that feels boredom could be driven to explore new areas instead of repeating old paths. Some researchers have even imagined giving these machines simulated emotions, not for drama, but for function. Emotions in humans help us prioritize. Fear protects us. Curiosity pushes us forward. Sadness helps us slow down and reassess. In a distant, lonely environment, a machine that can simulate some of these traits might perform better than one that's purely logical. It might avoid falling into the same error loop or ignoring subtle signs of trouble. As the technology improves, the line between tool and traveler begins to blur. A machine that makes decisions, improves itself, and responds to the world is no longer just a hunk of metal. It's not a person, but not just a program either. It becomes a kind of digital pioneer, shaped by Earth, but separate from it. And as these explorers go farther, we may find that they become our eyes, ears, and minds in places we may never reach. The first truly autonomous astronaut might be a small, silent craft skimming above alien ground, its sensors alive with thought. It might walk, roll, or fly, collecting data and solving problems with no help from Earth. It won't need food, air, or comfort, but it will need knowledge, and if we give it enough, it may go farther than any human ever will. If the stars are our destination, what becomes of Earth? If humanity ever becomes a spacefaring civilization in the true sense, what does that mean for the place we came from? Earth, for all its history, might no longer be the center of our story. It could become a distant point of origin, known by name, but rarely visited. What Earth becomes in a future where the stars are reachable depends a great deal on the path we take to get there. In some visions, Earth thrives. It becomes a cultural hub, a wellspring of art, philosophy, and heritage. In these futures, Earth is not abandoned, but celebrated. People might leave to explore and settle other worlds, but they still look back to Earth as a kind of spiritual homeland. In this version, Earth becomes like ancient Athens or Mecca, less a seat of power than a source of origin. Maybe not everyone would return physically, but they might return in thought, through stories, traditions, and digital archives that preserve what Earth once was and what it still means. In this kind of future, Earth could even become a kind of museum world. Cities might be preserved not for their function, but for their history. The Amazon rainforest, the Great Barrier Reef, or the ruins of human civilizations could be restored and maintained, not just by humans, but by automated systems designed to keep the memory of Earth alive. Visitors from other planets might walk through open-air exhibits under Earth's blue sky, learning about where humanity began. Earth might be slow, quiet, and even sparsely populated, but still cared for, like a cultural archive. It could also serve as a hub for tourism. Even if faster-than-light travel remains impossible, Improved propulsion and infrastructure might make the solar system a well-traveled region. Think of it like Venice, Kyoto, or Machu Picchu, places people go to feel the weight of time. Spaceborne humans might come to Earth to touch real soil, see real oceans, or experience gravity for the first time. Earth's biodiversity might be unmatched anywhere else, and that alone could draw travelers from the colonies. Its cultural depth, thousands of years of music, literature, cuisine, and language, might make it feel ancient and rich, even if it's no longer the political or economic core. Some imagine that Earth, if left mostly to itself, might undergo a kind of ecological rewilding. As humans move off-world, cities could empty, and forests could return. Animals might reclaim territory. Projects to clean the oceans and restore the air could be carried out with the help of advanced automation. If the pressure of population drops, Earth could recover from the scars of the industrial age. It might even become more beautiful than it has been in centuries. But there are other, darker possibilities. In some versions of the future, Earth is not a preserved sanctuary, but a world left behind. Colonization of other stars might not be a united mission, but a desperate escape. If climate change, resource collapse, or political instability worsen, the first ships to leave Earth might not be explorers, but refugees. In that case, Earth becomes a fading memory, a place people speak of in past tense. Later generations might know it only through scraps of data or distorted myths. They might not even believe it was real. There are also futures where Earth becomes a kind of underclass. In a galaxy of thriving colonies with advanced economies and stable systems, Earth might lag behind. Its people might be poor, its infrastructure failing. Wealth and knowledge might flow outward, toward the stars, while Earth declines into a kind of neglected shell. In these versions, Earth becomes less like a museum and more like a forgotten suburb, barely connected to the systems it helped create. Even in scenarios where Earth survives, the psychological distance might grow. If a colony around Alpha Centauri, Proxima b, or Tau Ceti builds its own cities and governments, it might begin to see Earth as just another planet. Over time, the cultural connection might fade. Languages could change. Religion might evolve. What Earth meant to the original travelers might not mean much to their great-grandchildren. They might learn about it the way schoolchildren today learn about ancient Rome, fascinating but distant. In some extreme cases, Earth might even be deliberately sealed off. If a future civilization decides that the planet needs to heal, or that it has become too unstable, it might place restrictions on access. Only a few people might be allowed to live there. Others might have to apply for limited permits. The surface might be monitored or protected by satellite systems. Some thinkers imagine the Earth as a spiritual site. Just as early humans treated certain caves, rivers, or mountains as sacred, future humans might create rituals around Earth, craft pilgrimages, or even invent new philosophies that center Earth as a holy place. In a universe full of alien planets and synthetic environments, Earth's systems, its winds, seasons, and rain, might take on mystical meaning. For people raised in domes or hollowed-out asteroids, the sight of a thunderstorm might feel like witnessing magic. Whether it ends up as a sanctuary, a shrine, a ruin, or a footnote will say more about us than about Earth itself. The Great Silence. Why haven't we seen others try? The universe is filled with hundreds of billions of galaxies, each with hundreds of billions of stars. Many of those stars have planets. Some of those planets may be Earth-like. If interstellar travel is even remotely possible, and if intelligent life has evolved elsewhere, it seems logical to expect signs of others. But when we look out, we see nothing. No starships crossing between systems. No radio signals drifting through the cosmic background. No glowing cities on distant worlds. Just silence. Deep, persistent silence. This puzzle is what physicist Enrico Fermi famously asked about in the 1950s. Where is everybody? If intelligent life is common, and space travel is even a little bit doable, then at least one species should have expanded, settled new systems, and left some kind of footprint we can see. But they haven't. Maybe Earth is not only unique in our solar system, but one of the only places in the galaxy, or the universe, where life got started at all. For all our searching, we have yet to find solid proof of life anywhere else, even simple microbes. Mars shows signs that it once had water, but no fossils. Europa and Enceladus might have oceans under their ice, but we haven't drilled into them. It's possible life is so difficult to create that it has only happened once here. Or perhaps life is fairly common, but intelligent life is rare. On Earth, life appeared early, but it took over 3 billion years to go from simple cells to complex animals. Even then, intelligent tool-making species only emerged in the last few 100,000 years. For most of Earth's history, life has been microbial. If that pattern holds across the galaxy, then even planets with life may never develop civilizations. But even if intelligence is rare, it only takes one civilization to begin exploring. So some researchers argue that the problem isn't life or intelligence, but the difficulty of traveling between stars. Maybe this is too much to ask. Maybe civilizations reach a certain level, look at the cost and complexity of interstellar travel, and decide it's not worth it. They stay home. They focus on virtual worlds, energy use, or local colonization. They send out radio waves for a few decades, then go quiet. And we miss them entirely. There's also the issue of time. The galaxy is around 13 billion years old. Humanity has been using radio for just over 100. That's a blink. If other civilizations appear and vanish in similar timeframes, the chance of two existing at the same time and noticing each other is small. We may not be alone. We may just be late. Or early. Some suggest that once civilizations become advanced, they tend to destroy themselves through war, environmental collapse, or runaway technology. It's not a comforting thought, but it could explain the silence. Maybe every species that reaches a certain stage faces the same risks. Maybe space is quiet because intelligent life, once it becomes powerful enough to reach out, is also powerful enough to end itself. Another possibility is that the galaxy is already full of probes or signals, but we're not looking in the right way. Maybe alien signals don't use radio at all, or use types of communication we haven't thought of yet, like modulated neutrinos, gravitational waves, or quantum entanglement. Our tools might be too primitive to detect them, or the messages might be hidden in ways we can't decode. The Great Filter theory suggests that somewhere along the path from life to intelligent spacefaring civilization, there's a barrier, something hard to cross. That barrier might be behind us. Maybe the leap from cells to conscious minds is rare. Or it might be ahead. Maybe interstellar travel is impossible. Or maybe self-destruction is almost guaranteed. If the filter is behind us, then we may be special. If it's ahead, we may be doomed. The answer matters a great deal, and right now, we don't know. It's also worth asking whether we would recognize alien activity if we saw it. A star being dimmed in a strange way might be a dust cloud or a giant energy structure. A signal with a strange pattern might be a pulsar or a message. Our own past shows how easy it is to mistake one for the other. Pulsars, for instance, were first labeled as LGM for little green men when discovered. They turned out to be natural, but that moment of confusion reminds us how limited our understanding still is. Despite the silence, many people continue to search. The SETI project, and others like it, keep listening for signals. New telescopes are scanning the sky with better resolution and wider ranges. Researchers are now looking for techno-signatures, the glow of cities, patterns of energy use, or waste heat from alien industries. If we can't hear them, maybe we can see their impact. But until then, we're left with silence and questions. Are we alone? Are we the first? Or just one of many, scattered across the stars, all waiting, all listening, all wondering if anyone else is out there? How would you rate humanity's chances of expanding its presence across the solar system and beyond? Send us your thoughts in the comments, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.